At first, the world seems solid. A stone lies where it lies. A planet circles where gravity carries it. A star burns in the distance, sending its light across the dark. A hand reaches for a cup, and the cup is either there or it is not. The everyday universe appears to be made of things with locations, shapes, speeds, and histories. Things seem separate from one another. A pebble on a beach is not the same thing as a mountain. A candle in one room is not the same thing as a star on the far side of the galaxy. Distance feels real. Separation feels obvious. This is the world our senses were built to understand. It is the world of footsteps, rain, fire, shadows, tides, and moons. It is the world where causes come before effects, where messages take time to travel, where something happening here cannot instantly change something happening far away. It is the world where an object can be hidden behind a door, but we still imagine it has some definite state while no one is looking. The door may hide it from us, but not from reality itself. For most of human history, this seemed natural. The universe appeared to be a great clockwork of matter and motion. If one could know every position and every speed, perhaps one could know the future. The moon moved because gravity pulled it. The tides rose because the moon and sun tugged on Earth's oceans. A comet returned because it followed an orbit. A thrown stone curved because Earth drew it downward. There was mystery. But it was mystery inside a universe that seemed, at its deepest level, definite. Then, in the study of light and atoms, the old certainty began to soften. The change did not happen all at once. It came slowly through strange clues. Light, which had long been understood as a wave, sometimes behaved as though it came in tiny packets of energy. Matter, which seemed solid and particle-like, sometimes behaved like a wave. Electrons, photons, and atoms did not follow the gentle expectations of everyday objects. They obeyed a quieter, stranger set of rules. These rules became quantum mechanics. Quantum mechanics is the science of the smallest known behavior of nature. It describes atoms, electrons, photons, and the particles and fields beneath the visible world. It is not a vague idea or a mystical suggestion. It is one of the most successful scientific theories ever created. It explains the structure of atoms, the chemistry of matter, the light of stars, the behavior of semiconductors, the working of lasers, and much of the technology hidden inside modern life. And yet, even though it works with extraordinary precision, it does not feel like the world we know. In ordinary life, a thing is where it is. In quantum mechanics, a particle can be described by a spread of possibilities. It may not have one sharply defined position in the way a grain of sand seems to have. Instead, before measurement, quantum theory gives probabilities. It tells us where a particle may be found, not always where it already is in the ordinary sense. This does not mean the particle is simply a tiny ball hiding somewhere and we are too clumsy to know its position. At least, quantum mechanics does not require that picture. The theory describes the particle with a wave function, a mathematical object that contains the possible outcomes of measurements. When we ask certain questions of the particle, nature gives an answer. But before the answer is obtained, the quantum state may contain many possible outcomes at once. This is called superposition. The word can sound mysterious, but the idea can be approached gently. A quantum object can be in a state that is not simply one ordinary option or another, but a combination of possible states. An electron can be described as having multiple possible positions. A photon can be described in terms of multiple possible paths or polarizations. A tiny quantum system can carry possibilities together in a way that has no perfect everyday comparison. This does not mean that large everyday objects are floating around in obvious magical mixtures. Stones, cups, trees, and people interact constantly with their surroundings. They become entangled with air, light, heat, and countless other particles. Their quantum possibilities become effectively hidden from ordinary experience through a process called decoherence. The everyday world emerges from the quantum world, but it does not show its strangeness easily. The quantum world is quieter than that. It does not announce itself in furniture or mountains. It waits in atoms. It waits in light. It waits in the hidden behavior beneath everything visible. One of the oldest clues came from light itself. Light can spread like a wave, producing interference patterns, soft bands of brightness and darkness where waves add together or cancel. But light can also arrive in individual packets called photons. When a beam of light is made very faint, the photons may arrive one by one, like tiny events striking a detector. And yet, over time, they can still build a wave-like interference pattern. It is as though each photon is not simply a little marble passing through one opening or another, but something described by a wave of possibilities. When it is detected, it appears at one place. But before detection, its quantum description may involve multiple paths. The same strangeness appears with electrons and other particles. In certain experiments, electrons can also create interference patterns, even when sent one at a time. Matter itself, at small scales, carries wave-like behavior. This is not because electrons are secretly ordinary waves in water or air. They are quantum objects. They are not exactly waves and not exactly particles in the everyday sense. They belong to a deeper category, and our familiar words only approximate it. A photon is not a tiny billiard ball. An electron is not a small planet orbiting like Earth around the Sun. An atom is not a miniature solar system. The images help at first, then they fail. The true quantum world is described by mathematics, but its meaning has troubled physicists for more than a century. What is a quantum state? Does measurement reveal a property that already existed? Or does measurement help bring one outcome from a range of possibilities? Is the wave function something real, or is it a tool for predicting what we will observe? Different interpretations answer these questions differently, and not all physicists agree on the deepest meaning. But the predictions work. Again and again, nature follows the quantum pattern, and among all quantum patterns, one is especially strange: entanglement. Entanglement begins when two quantum systems become described not as separate things with separate states, but as one shared state. The particles may later move far apart. They may travel in opposite directions. One may be measured in one laboratory and the other in another laboratory far away. But the best quantum description of them remains joint. The whole system has properties that cannot be reduced to each particle alone. This is the heart of the mystery. Two particles can become linked, not by an invisible rope, not by a radio signal, not by a tiny message passing between them in space, but by the structure of their shared quantum state. To approach this slowly, imagine a source that creates two particles together. The particles fly away from each other. One travels to the left, one travels to the right. Each particle is measured later. Perhaps the measurement concerns polarization, if the particles are photons. Perhaps it concerns spin, if the particles are electrons or similar quantum systems. Spin is not exactly like a little planet spinning on an axis, though the word suggests that image. It is a quantum property, a kind of intrinsic angular momentum. When measured along a chosen direction, a spin can give certain possible outcomes. For a simple spin system, one might find an outcome often called up or down, depending on the measurement direction. Now suppose the two particles are entangled in such a way that their measurement results are strongly correlated. If one result is found to be up, the other may be found to be down when measured in the same way. The strange part is not merely that the results match or oppose each other. Ordinary objects can also be correlated. If someone places one red glove in one box and one blue glove in another, then sends the boxes far apart. Opening one box immediately tells you something about the other. If you find the red glove here, you know the blue glove is there. That is not mysterious. The gloves had their colors all along. You simply did not know which box contained which glove. Entanglement is deeper than that. In quantum mechanics, for certain measurements, it is not correct to imagine that each particle simply carried a complete list of fixed answers all along, at least, not if those answers are local and ordinary in the classical sense. The correlations between entangled particles can be stronger than any allowed by a simple hidden instruction picture. This deeper claim was later made precise through Bell's theorem and tested in experiments. But the mystery begins with a simple idea that two particles can share one quantum state even across distance. Before measurement, quantum theory may not assign each particle its own definite value for every possible measurement. Instead, it assigns a joint state to the pair. When one particle is measured, the outcome is random in a way we cannot control. But when the other particle is measured in a corresponding way, its result is correlated with the first. The results are not controllable. This is essential. Entanglement does not allow faster-than-light messaging. One observer cannot choose the result of a measurement and use it to send a signal instantly to another observer. Each local result appears random. Only when the two observers later compare their results through ordinary communication, limited by the speed of light, do the correlations become clear. So entanglement does not break the rule that usable information cannot be sent faster than light. And yet, it still unsettles the ordinary idea of separateness, because the correlations are not easily explained by the old picture of two independent objects carrying definite properties from the start. This is why entanglement feels like a hidden doorway in physics. It respects the structure of relativity in the sense that it cannot be used to send messages faster than light. But it also suggests that quantum reality is not built from isolated parts in the simple way everyday experience suggests. The whole can be more fundamental than the pieces. Two particles, once entangled, may be best understood as one system even when separated. This does not mean they are connected by a visible thread through space. It does not mean one particle whispers to the other. It does not mean consciousness is required to make them real. It means the mathematical state that describes them cannot be factored into two independent states. Their properties, as measured, belong to a shared quantum structure. The mystery is quiet but profound. A pair of entangled particles can be separated by a room, by a city, by hundreds of kilometers, or in principle by far greater distances. The quantum correlations remain, as long as the entanglement is preserved and not destroyed by interactions with the environment. In practice, entanglement is delicate. It can be lost when particles interact with surrounding matter, stray light, heat, or noise. This is one reason quantum experiments are so carefully controlled. The world around us is full of interactions. A photon scatters. An atom vibrates. A detector absorbs light. A molecule collides with air. Each interaction can spread quantum information into the environment. The clean, fragile relationship between entangled systems can become entangled with countless other systems, making the simple pair no longer usable in the same way. This is one reason the everyday world looks classical. Not because quantum mechanics disappears, but because its delicate patterns are constantly dispersed into the vast environment. Still, in laboratories, physicists can create and preserve entanglement long enough to study it. They can entangle photons, atoms, ions, superconducting circuits, and other systems. They can measure correlations with careful precision. They can send entangled photons through optical fibers or through open air. They can use entanglement as a resource for quantum information. But before its applications, entanglement was a problem of meaning. It asked what kind of world we live in. Is reality made of separate objects with complete properties, merely hidden from us until we look? Or is there something about the quantum state that refuses to be divided into independent pieces? To feel the strangeness, return to the image of two particles moving apart, They begin together in one shared state. They drift away into darkness. One enters a detector here. The other enters a detector far away. The measurement here gives one result, the measurement there gives another. Individually, each result looks random, but together they show a pattern, as if the two events belong to one deeper reality. Distance has not erased the relationship. Space has stretched between them, but the quantum state still carries a connection of correlation. No signal needs to pass from one to the other in the ordinary sense. No message can be controlled. No faster than light communication is possible, and still the pattern remains. This is what made entanglement feel so disturbing to Albert Einstein. Einstein had helped create quantum theory. He explained the photoelectric effect by proposing that light could behave as packets of energy, later called photons. He understood deeply that the world of atoms required new ideas. But he was never comfortable with the thought that quantum mechanics, as usually understood, was complete. Einstein valued locality, the idea that what happens here should not instantly affect what is real over there. He valued a kind of realism. The idea that physical things should possess definite properties independent of observation, at least in some deeper description. Quantum mechanics seemed to challenge both. For Einstein, the problem was not merely that quantum mechanics was strange. Many true things are strange. The problem was that it seemed to leave reality unfinished. It gave probabilities rather than definite underlying events. It described correlations between distant systems in a way that seemed to him almost like a ghostly influence across space. He famously criticized this kind of idea as spooky action at a distance. The phrase has become one of the most repeated in all of physics, but it should be handled carefully. Entanglement is not magic. It is not supernatural. It is not a mystical force. It is a precise feature of quantum mechanics. The word spooky captures the discomfort, not the scientific explanation. Einstein's discomfort was powerful because he was not confused about physics. He saw the issue clearly. He understood that if quantum mechanics were complete, then nature might be stranger than the older worldview allowed. If it were incomplete, then perhaps deeper hidden variables existed, restoring a more familiar reality beneath the probabilities. This question would become one of the greatest scientific puzzles of the 20th century. But before Bell's theorem, before the experiments, before the Nobel Prizes in quantum information technology, there was the simple unease of the idea itself. Two particles, one shared state, a measurement here, a correlated result there, randomness locally, order together, distance preserved, yet separateness questioned. This is why entanglement is often called the strangest feature of quantum mechanics. It is not just another oddity. It reaches into the meaning of reality. It asks whether the world is built first from individual things or from relationships that cannot always be broken apart. In everyday life, relationships are usually secondary. Two stones may sit near each other, but each stone seems to have its own existence. Two stars may orbit in a binary system, but each star has its own mass, light, and history. Two people may be connected by memory, language, or love, but physically they remain distinct bodies in separate places. Quantum entanglement suggests that, at the smallest scales, the relationship can be part of the physical state itself. The pair is not merely two things we happen to discuss together. The pair can be one quantum object, even when distance grows between its parts. This does not mean the particles lose all individuality in every sense. Each can be detected locally. Each can produce a measurement event, but the complete description belongs to the pair. The properties revealed by measurements cannot always be understood as belonging independently to each particle before measurement. This is where language begins to strain. The quantum world does not fit easily into ordinary words because ordinary words were shaped by ordinary experience. We say particle, but imagine a little object. We say wave, but imagine water. We say spin, but imagine rotation. We say measurement, but imagine looking. We say connection, but imagine a signal. Each image helps for a moment, then it becomes too small. Quantum mechanics requires us to be careful. Measurement does not have to mean a human mind looking at something. It means a physical interaction that extracts information and produces an outcome in a measuring apparatus or environment. Entanglement does not mean emotional connection or cosmic consciousness. It means a specific mathematical relationship between quantum states. Superposition does not mean a particle is simply doing everything in an ordinary way. It means its quantum state combines possible outcomes until a measurement yields one. The wonder is stronger when the science is kept clear, because the real idea is already strange enough. One of the gentlest ways to picture entanglement is not as a thread, but as a shared song. Imagine two notes created from the same melody. The notes travel into separate rooms. Heard alone, each note may seem uncertain, incomplete, or random. But when the two are compared, a deeper pattern appears. The melody was never in one note alone, it was in the relationship. This is only a metaphor, and like all metaphors, it eventually fails. But it points toward the central feeling. In entanglement, the relationship is not merely something we notice afterward, it is built into the state. The whole carries information that the parts alone do not. This is not unique to philosophy, it is used in modern physics. Entanglement is central to quantum information science. It helps make quantum teleportation possible, though that phrase does not mean teleporting a person or object. It allows the transfer of an unknown quantum state using shared entanglement plus ordinary classical communication. Entanglement also plays a role in quantum cryptography and quantum computing, where correlations and superposition may allow certain tasks to be performed in new ways. But these technological ideas come later. At the beginning of the documentary, the most important thing is to feel the quiet shift. The universe is not only made of solid things in definite places. At its deepest tested levels, it is described by probabilities, quantum states, and relationships that do not always fit the classical picture. A photon can behave like a wave and arrive like a particle. An electron can be described by a spread of possible positions. Two particles can share one state. Measurement can reveal outcomes that were not simply waiting like colored gloves and boxes, and the universe beneath its calm surface seems to hold a kind of hidden delicacy. Think of the visible world again, a quiet room, a book on a table. Moonlight at a window, a distant star, everything appears settled. But inside the table, atoms are held by quantum rules. Electrons occupy orbitals, not little planetary paths. Chemical bonds exist because of quantum behavior. The light in the room arrives as photons. The warmth in the air is carried by countless molecular motions and electromagnetic interactions. The solidity of the table is not true, solidity in the simple sense, but the result of forces, quantum states, and the exclusion principle that prevents electrons from all collapsing into the same state. The ordinary world is a calm surface above an invisible quantum sea. Most of the time, the sea is hidden. But in careful experiments, it reveals itself. A single photon is sent toward a pair of paths. A pattern appears. An atom emits light in discrete energies. A detector clicks. Two particles are created together. They separate. Measurements are made. The results are random alone, but correlated together. The quantum sea speaks in probabilities. And when it speaks through entanglement, it speaks of a world where distance is not enough to make everything independent. This is not the same as saying distance is unreal. Distance is real in physics. Space matters. Relativity matters. Signals still cannot outrun light. If two observers want to compare their measurements, they must communicate normally, and that communication takes time. The universe does not let entanglement become a device for instant messages across the stars. but the correlations remain, and that is enough to disturb the older view. The old classical dream imagined a universe where every property existed in advance, every event unfolded from local causes, every uncertainty came only from ignorance. Quantum mechanics does not fit that dream. It offers a different kind of order. Not the order of perfect prediction for each event, but the order of precise probabilities. Not the order of isolated objects with all properties fixed, but the order of states, measurements, and correlations. The universe is not less lawful. It is lawful in a stranger way. This is why quantum mechanics can be both deeply reliable and deeply unsettling. It lets scientists calculate results with extraordinary accuracy. It powers real devices. It predicts spectral lines, atomic behavior, and particle interactions. Yet it leaves us asking what is really happening when a quantum system is measured. It leaves us asking whether the wave function is a physical thing or a description of knowledge. It leaves us asking how reality becomes definite. Entanglement sharpens all of these questions because it forces the mystery to cross distance. A single particle in superposition is strange enough, but a pair of entangled particles makes the strangeness harder to dismiss as merely local confusion. It shows that the quantum description of the whole can remain unified even when the parts are far apart. For Einstein, this was unacceptable as a final description. He did not deny the experimental success of quantum mechanics. He did not reject its usefulness. But he believed it might be incomplete. Perhaps he thought there were deeper variables beneath the quantum state, hidden facts that determined outcomes in advance. If only we knew those hidden facts, the randomness would disappear and the distant correlations would no longer seem spooky. This was a reasonable hope. It preserved locality. It preserved realism. It preserved the idea that the moon is there when no one looks, and that particles have definite properties whether or not we measure them. But nature would not make the answer easy. For decades, the debate seemed almost philosophical. Einstein and Niels Bohr argued about the meaning of quantum mechanics in some of the most famous exchanges in scientific history. Bohr defended the completeness of the quantum description, emphasizing the role of measurement and experimental arrangement. Einstein pressed the question of whether the theory could really be the final word. The disagreement was subtle. It was not a simple battle between genius and error. It was a deep argument about what physics should mean. Should a theory merely predict observations? Should it describe an underlying reality? Can nature be fundamentally probabilistic? Can distant particles share a state without violating relativity? Are properties real before measurement? What counts as a complete description of the world? These questions began in the smallest particles, but they opened into the largest possible ideas. Because if quantum mechanics is telling us something true about reality, then separateness itself is not as simple as it appears. The universe may not be built from isolated pieces first, with relationships added later. At least in some cases, the relationship may come first. The whole may be the thing nature knows most clearly. Imagine again the two particles. They are created together in a shared state. They move apart. Perhaps one travels through fiber or open space to a distant detector. Perhaps the other remains nearby. The distance between them grows. In ordinary thinking, they should now be separate objects, each carrying its own full set of properties. But quantum mechanics says the pair may remain one system. The first detector registers an outcome, the second detector registers an outcome. The outcomes cannot be used for instant messaging, but when compared they reveal the hidden pattern. The particles behave not like two classical coins secretly chosen in advance, but like parts of a quantum state whose correlations exceed classical explanation. This is the doorway into the rest of the story. Part of the mystery is already here. The quantum world does not behave like tiny furniture. It does not merely shrink the ordinary world to microscopic size, it changes the rules. And once the rules change, the meaning of distance, knowledge, and reality changes with them. There is something calming in this, despite its strangeness. The universe does not need to match human intuition. It is allowed to be deeper than the senses that evolved on one small planet. We learned the world first through touch, sight, weight, and motion. But atoms do not owe us familiarity. Photons do not need to behave like pebbles. Reality is not required to be simple just because the everyday world feels simple. The quantum world is not chaos. It is a hidden order, a soft order of amplitudes, probabilities, and correlations. A world where the possible is structured before the actual appears. A world where measurement is not passive in the old sense. A world where two particles can share one description, and from this hidden order, the visible universe rises. Every star shines because quantum processes allow nuclear fusion and radiation. Every atom holds together through quantum rules. Every chemical bond, every crystal, every molecule of water, every strand of DNA, every metal, every cloud, every living cell exists because the quantum world behaves as it does. The strangeness is not far away. It is the foundation. Even the calmest night sky is quantum at its roots. The light from a star comes as photons. Those photons may have been born in the hot matter of a stellar atmosphere, then traveled for years, centuries, or millions of years through space before entering an eye or a telescope. Each photon carries energy. Each photon obeys quantum rules. The starlight that seems so smooth is made of countless quantum events. The universe is not only vast, it is subtle. At the largest scales, gravity gathers galaxies into clusters and filaments. At the smallest scales, quantum mechanics shapes matter and light. Somewhere between these scales, planets form, oceans gather, and life appears. The human mind lives in the middle, trying to understand both the cosmic and the quantum. Entanglement is one of the places where that understanding becomes most difficult and most beautiful. It tells us that the universe is not simply a collection of separate little parts. It tells us that relationships can be physically fundamental. It tells us that measurement, probability, and correlation are woven into the behavior of nature. It tells us that even when distance is real, separateness may not be complete. This is why the story of entanglement is more than a story about particles. It is a story about what kind of reality lies beneath appearances. In the ordinary world, things seem separate. In the quantum world, some things are described together. In the ordinary world, uncertainty often means ignorance. In the quantum world, uncertainty can be part of the state itself. In the ordinary world, a measurement reveals what was already there. In the quantum world, measurement is tied to the emergence of a particular outcome from a range of possibilities. In the ordinary world, distance makes independence feel natural. In the quantum world, entanglement shows that distance alone does not always separate a shared state, and so the first part of the journey brings us to a quiet edge. Behind the visible universe, beneath stars and stones and breath and darkness, there is a layer of reality where the familiar rules loosen. Light becomes both wave-like and particle-like. Matter becomes described by probability. Possibilities overlap. Measurement matters. And two particles, once joined in the right way, can remain part of one quantum description even after space opens between them. Einstein saw this edge clearly. He did not turn away from it because he failed to understand it. He turned toward it because he understood how serious it was. If quantum mechanics was complete, then the universe was stranger than the old classical dream. If it was incomplete, then hidden beneath quantum probabilities, there might be a deeper order still waiting to be found. Either answer would change physics. Either answer would change the meaning of reality. And so the mystery passed from the quiet behavior of particles into one of the greatest debates in science. a debate about whether the world is complete as quantum mechanics describes it. A debate about locality, realism, and hidden variables. A debate about whether the strange link between particles is truly part of nature, or only a sign that something deeper remains unseen. Two particles drift apart. One state describes them. A measurement waits in the dark. And somewhere in that silence, the old certainty of the separate world begins to fade. Einstein did not dislike mystery. He had built much of his life around it. As a young man, he had imagined what it would be like to chase a beam of light. He had questioned time, space, motion, and gravity. He had shown that clocks do not tick the same for everyone, that mass and energy are deeply related, and that gravity is not merely a force pulling across emptiness, but a curve in the fabric of space-time itself. Einstein was not afraid of strange ideas. He had made the universe stranger. But the strangeness of quantum mechanics troubled him in a different way. Relativity had transformed the world, but it had not made the world feel unfinished. In relativity, events still happened in a clear order inside space-time. Causes did not outrun light. Objects followed paths. Clocks slowed, distances changed, gravity bent light, but the universe remained deeply ordered. It was surprising, but not careless. It was strange, but not vague. Quantum mechanics felt different. It did not simply say that the universe was stranger than expected. It seemed to say that at the deepest level, nature did not always possess definite answers before being measured. It seemed to replace certainty with probability and clear properties with possible outcomes. It worked beautifully, but to Einstein it did not seem complete. He accepted that quantum mechanics was powerful. He accepted that it predicted experiments with remarkable success. He had helped begin the quantum revolution himself, but he did not believe that the theory, as it stood, gave the final picture of reality. For Einstein, physics was not only about predicting what an observer would see. It was about describing a world that existed whether or not anyone looked. The moon was there even when no one saw it. A particle, he believed, should have some reality of its own, not only a list of probabilities waiting for measurement. He was not alone in this discomfort. The early 20th century was filled with physicists trying to understand what the new quantum theory meant. Niels Bohr, Werner Heisenberg, Max Born, Erwin Schrödinger, Paul Dirac, Louis de Broglie, and many others had helped shape a theory that worked, but the meaning of its success remained deeply debated. Bohr, in particular, became one of Einstein's great intellectual opponents. Their disagreement was not loud in the ordinary sense. It was careful, deep, and persistent. They argued through letters, conferences, thought experiments, and philosophical pressure. Each man saw something profound in the theory, but each wanted a different kind of answer from nature. Bohr accepted that quantum mechanics forced a new view of measurement and knowledge. He argued that we must speak carefully about what can be observed, and that the experimental arrangement matters. We cannot simply imagine tiny particles carrying every familiar property in the old classical way. The act of measurement is not a minor detail, it is part of how quantum phenomena become definite to us. Einstein wanted more. He wanted a description beneath the measurement, a deeper layer, a reality that did not depend on which experiment we chose to perform. To him, a complete theory should describe what exists, not only what may be found if we ask nature a certain question. This disagreement became sharper because of entanglement. Entanglement took the uneasiness of quantum mechanics and stretched it across space. A single particle in superposition was strange enough. But perhaps, Einstein thought, the uncertainty of a single system could be understood as ignorance. Perhaps the particle had some hidden properties we did not yet know how to describe. Perhaps quantum mechanics was like a weather forecast, giving probabilities only because we lacked a deeper knowledge of the true conditions. But two entangled particles made the problem harder. If quantum mechanics was right, two particles could share a single state. They could move apart, far away from each other, and yet measurements on them would show correlations stronger than any ordinary classical explanation seemed to allow. Einstein saw a danger here. If measuring one particle could appear to define the state of the other, even when the second particle was far away, what did that mean? Did something happen instantly across distance? Did the measurement here somehow affect the reality there? Or did both particles already carry hidden information from the beginning? Einstein strongly preferred the last possibility, not because it was simple, but because it preserved a principle he considered essential: locality. Locality is the idea that objects are influenced directly only by their immediate surroundings, and that no physical influence should travel faster than light. In relativity, this is fundamental. The speed of light is not only the speed of light itself, but the speed limit for cause and effect. If something happens here, its influence cannot instantly appear in a distant place. It must travel outward, limited by the structure of space-time. Locality protects the order of the universe. It prevents cause and effect from becoming tangled in contradictions. It means that distant things cannot simply reach through space and change one another without something passing between them. Einstein also cared about realism. Realism, in this context, is the idea that physical systems possess real properties independent of observation. A particle's properties should not be created merely by looking. A distant object should have a state of its own. Measurement should reveal reality, not bring reality into being from nothing. Together, locality and realism formed a natural worldview. Things are real, things are separate. Causes travel through space no faster than light. Measurements reveal what is there. This is close to how the everyday world feels. Quantum mechanics seemed to threaten it, and entanglement threatened it most sharply. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a famous paper that became known by their initials, EPR. The paper was not an attack on quantum mechanics as a useful tool. It was a challenge to the claim that quantum mechanics was a complete description of physical reality. The EPR argument was subtle. It asked what should count as an element of reality. If you can predict with certainty the value of a physical quantity without disturbing the system, then, they argued, there must be something real corresponding to that quantity. In the thought experiment, two systems interact and then separate. Because of the way quantum mechanics describes them, measuring one system can allow you to predict something about the other. But if the two systems are far apart, and if no signal can pass instantly between them, then measuring the first system should not disturb the second one. So, if you can predict a property of the distant system without disturbing it, perhaps that property must have been real already. But quantum mechanics did not assign all such properties definite values at the same time. Therefore, EPR argued, quantum mechanics must be incomplete. There must be more to reality than the quantum state describes. This was the core of Einstein's challenge. It was not merely, quantum mechanics is strange, so I dislike it. It was more precise. If quantum mechanics is complete, then distant measurements seem connected in a way that threatens locality. If locality is preserved, then quantum mechanics does not provide a complete description. Something is missing. Einstein wanted the missing something. He wanted hidden variables, or some deeper theory, that would restore a more definite reality beneath quantum probabilities. The phrase hidden variables can sound mysterious, but the idea is simple. Suppose quantum mechanics gives only probabilities because it does not know the full state of the system. Beneath the wave function, perhaps there are additional facts hidden from us that determine what outcome will occur. Just as a coin toss seems random if we do not know the exact force, angle, spin, air resistance, and surface it lands on, perhaps a quantum measurement seems random only because we do not know the deeper details. If such hidden variables existed, then particles might carry definite instructions all along. The randomness would be ignorance. The correlations would be prearranged. The world would be strange, but not as strange as quantum mechanics seemed to suggest. Return to the image of two boxes. If one contains a red glove and one contains a blue glove, opening one box tells you immediately what is in the other. But nothing spooky has happened. The gloves were placed in the boxes before they separated. Your discovery here does not change the glove there. It only changes what you know. Einstein hoped that entangled particles might be like that in some deeper way, not literally gloves, not simple classical objects, but perhaps carrying some hidden information that quantum mechanics had not included. Then the distant correlations would not require any mysterious connection across space. They would simply reveal a deeper order established in the past. Bohr disagreed. He believed EPR had misunderstood what quantum mechanics was telling us. To Bohr, the conditions of measurement could not be separated from the phenomenon being measured. Quantum properties are not always like classical properties, waiting quietly inside objects. The experimental context matters. We must be careful not to impose everyday ideas onto a domain where they no longer apply. Bohr's response was famously difficult to understand, partly because the issue itself is difficult, and partly because Bohr's writing could be dense. But his basic position defended the completeness of quantum mechanics. He did not think EPR had shown that the theory was incomplete. Instead, he thought it revealed how deeply classical assumptions fail when applied to quantum systems. The debate became one of the great turning points in physics, not because it was immediately resolved. It was not. For decades, the question remained suspended between experiment, mathematics, and philosophy. Einstein had presented the challenge. Bohr had defended quantum theory. But there was not yet a clear experimental way to decide between the deepest versions of the two views. The EPR paper raised the question of whether quantum mechanics was complete, but it did not yet give an easy test that could settle the issue. The hidden variables Einstein imagined might exist in some unknown form. Quantum mechanics continued to work. Most physicists used it successfully and moved on to other problems. But the question remained. Was the quantum world truly indeterminate in the way the theory seemed to say? Or were there hidden facts beneath the surface? Were entangled particles connected by a strange, shared quantum reality? Or were their correlations only the result of instructions carried from the beginning? Could reality be both local and definite? Or did nature force us to give up something? This is where the story becomes especially quiet and profound. For a long time, entanglement was treated by many as a philosophical oddity. It was discussed in debates about interpretation, but it was not yet the central practical resource it would later become. The word entanglement itself was introduced by Schrödinger, who recognized it as one of the defining features of quantum mechanics. He saw that when two systems interact, their states can become linked in a way that cannot be described by separate individual states. Schrödinger understood that this was not a side effect, it was central. Entanglement was not one small strangeness among many. It was, in some ways, the essence of quantum mechanics. Still, the scientific culture of the time often focused on calculation. Quantum mechanics worked. It predicted spectra, atoms, molecules, solids, and radiation. Physicists could use it without agreeing on what it meant. The famous phrase, often summarized as "shut up and calculate," captures this practical attitude, though the history of the phrase itself is later and more complicated than the early debates. The attitude was understandable. The theory was too useful to ignore. But Einstein's discomfort did not disappear. He continued to believe that quantum mechanics was incomplete. He famously objected to the idea that God plays dice with the universe. The exact wording and context varied, but the meaning is clear. He resisted the idea that fundamental randomness was the final truth of nature. Bohr is said to have replied in spirit that Einstein should not tell God what to do. Whether framed exactly or not, the exchange captures the philosophical divide. Einstein wanted a deeper determinism. Bohr accepted quantum uncertainty as part of the structure of physical description. Neither was being careless. Both were trying to understand what reality demanded. The argument over entanglement can be seen as a conflict between two intuitions. The first intuition is that the world is made of separate things. If two objects are far apart, then what happens to one should not instantly change the other. Any influence must travel through space, limited by light. The second intuition is that quantum mechanics is telling us something true. If the mathematics says the pair has one shared state, and if experiments confirm the predicted correlations, then perhaps separateness is not as basic as it seems. Einstein trusted the first intuition deeply. Bohr trusted the quantum formalism and the lessons of measurement. The universe would eventually be asked to choose. But before the experiments came the thought experiments. A thought experiment is a laboratory of the mind. Einstein loved them. He had imagined elevators in free fall, trains and lightning strikes, clocks and light beams. His greatest insights often began with simple images sharpened into physical arguments. With EPR, the thought experiment became a way to reveal tension. Imagine two particles that once interacted and then moved far apart. Quantum mechanics assigns them a linked state. Depending on what you measure on the first particle, you can predict a corresponding property of the second. But if the second is far away, measuring the first should not disturb it, unless some influence travels faster than light. If it is not disturbed, and if you can predict its property, then perhaps that property was real all along. If quantum mechanics does not include that property as definite, then quantum mechanics is incomplete. This is the rhythm of the EPR argument. It moves slowly but forcefully. Locality, prediction, reality, incompleteness. The argument does not say quantum mechanics gives wrong predictions. It says quantum mechanics might not tell the whole story. That distinction is important. Einstein was not rejecting the evidence. He was questioning the interpretation. He wanted a theory that would reproduce the successful predictions of quantum mechanics while restoring a deeper reality. Such a theory would need to explain why the quantum probabilities work, but also why events have definite causes beneath them. In modern language, he wanted something like a local, hidden variable theory. Local because no faster than light influence should be needed. Hidden variable because additional underlying facts would determine the outcomes. For a while, it seemed possible. There was no obvious way to rule it out. Perhaps nature really had secret instructions under the quantum surface. Perhaps particles carried more information than the wave function described. Perhaps entanglement was only a sign of our incomplete knowledge. Then, decades later, John Bell would show that this hope could be tested. But that belongs to the next part of the story. For now, we remain with Einstein's problem. A problem that is easy to state gently, but difficult to escape. What is real before measurement? If a particle has no definite value until measured, what does measurement do? If two particles are entangled, why are their results so deeply correlated? If no signal travels between them, how does the whole pattern arise? If hidden variables explain it, what kind of hidden variables can survive experiment? These questions drifted through the middle of 20th century physics like quiet stars behind cloud. They did not stop quantum mechanics from advancing. Physicists built quantum electrodynamics. They developed nuclear physics, solid-state physics, particle physics, and technologies that depended on quantum rules. The mathematical machinery became extraordinarily powerful, but the foundational mystery remained, and entanglement waited. There is a strange patience in scientific questions. Some are answered quickly, Others wait for the right experiment, the right theorem, the right instrument, or the right mind. The question Einstein raised in 1935 waited nearly 3 decades for Bell's theorem. It waited longer still for increasingly precise experiments. And even now, after many strong tests, the meaning of quantum mechanics remains debated, though the old dream of simple local hidden variables has been profoundly challenged. Einstein did not live to see Bell's theorem published. He did not live to see the later experiments that would test the deep structure of entanglement, but his challenge shaped the path. Without EPR, the question might have remained less clear. Without Einstein's insistence, the discomfort might have been easier to ignore. His resistance did not stop physics, it sharpened it. This is one of the most important things to understand about Einstein's role in the story. It is tempting to tell the story as if Einstein was simply wrong and quantum mechanics was simply right. But that is too shallow. Einstein saw a real problem. He asked a deep question. He forced the theory to confront its own meaning. Even when nature later favored the quantum predictions, Einstein's challenge remained valuable. He made the mystery precise enough to become science. In the quiet debate between Einstein and Bohr, the universe became more than a collection of particles. It became a question about knowledge, reality, and the limits of separation. Bohr's view suggested that we must give up the dream of describing quantum objects with all classical properties at once. We cannot speak of certain properties independently of the measurement context. Reality at the quantum level does not behave like an unseen classical machine. Einstein's view insisted that physics should aim deeper. A theory that only gives probabilities without underlying reality felt incomplete. He believed there should be something more, something not yet found. Both men were guided by a sense of order, but they meant different kinds of order. Einstein's order was a world of definite reality beneath appearances. Bohr's order was a disciplined framework of what can be meaningfully said and measured. Einstein wanted the hidden world behind the observations. Bohr warned that the conditions of observation are part of the quantum phenomenon itself. The debate can feel abstract, but entanglement makes it vivid, because entanglement turns philosophical uncertainty into a scene. Two particles leave a common source. They separate. A measurement is made here. A measurement is made there. The results, considered separately, are random. The results, compared together, are correlated. The old worldview asks, what did each particle carry? The quantum worldview answers, the pair had one shared state. Einstein asks, but how can that be complete if the particles are distant? Bohr answers, because the classical demand for separate pre-existing properties is not valid in the quantum domain, and the universe remains silent, waiting for experiment. There is also a deeper emotional quality to Einstein's objection. He believed in intelligibility. He believed the universe could be understood as a coherent reality, not necessarily simple, not necessarily comfortable, but coherent in a way that did not depend on observers choosing questions and receiving probabilities. Quantum mechanics seemed to put a veil between the theory and reality itself. It said, in effect, here are the probabilities of what you will observe. Einstein wanted to know what is. That desire has never disappeared from physics. Even physicists who accept quantum mechanics completely may still ask what it means. Different interpretations continue to exist. Some accept wave function, collapse. Some imagine many worlds where all outcomes occur in branching realities. Some propose pilot waves where particles have definite positions guided by a wave. Some take more informational or relational views. Some avoid interpretation as much as possible. Entanglement sits at the center of many of these interpretations. It is the feature that any serious understanding of quantum mechanics must face, because it shows that the quantum state of a whole system can be inseparable. The parts alone are not enough. This idea now appears far beyond the EPR debate. entanglement has become important in quantum field theory, quantum computing, condensed matter physics, black hole physics, and even ideas about space-time itself. Some modern physicists suspect that entanglement may not merely happen inside space-time, but may help explain how space-time structure emerges. These are still deep and developing ideas, but they show how far Einstein's problem has reached. A question once treated by some as philosophical has become one of the central resources of modern physics. The ghost has become machinery. The discomfort has become technology. The paradox has become a tool. But in Einstein's time, the mystery was still raw. Imagine the scene not as a laboratory, but as a quiet room filled with thought, paper, equations, letters, conversations, a world still recovering from the shock that atoms were not simple, solid pieces of matter. A scientific generation trying to understand whether probability was fundamental or temporary. Einstein, already famous, already having reshaped space and time, looking at quantum mechanics and saying, "Not yet." This cannot be the whole story. Bohr, equally serious, saying, "Perhaps the demand for the old kind of story is the problem. Between them, entangled particles drift like a silent riddle." The riddle was not about whether quantum mechanics worked. It worked. It was about why it worked and what its success meant. If a theory predicts every experiment, does it need to tell us what reality is like when no one measures? Can a probability be fundamental? Can two distant particles be one system? Can measurement create definite outcomes? Can the universe be local, realistic, and quantum all at once? Einstein's answer leaned toward no. Quantum mechanics must be incomplete. Bohr's answer leaned toward yes, but only if we give up certain classical assumptions. The later answer from Bell would be more precise and more disturbing. Nature would not allow all the old comforts to remain. But we are not there yet. For now, we can rest inside the question. There is a calmness in not rushing to the conclusion. Einstein's problem deserves to be felt, because it is not only a problem for physicists, it is a problem for intuition itself. Everyday life teaches separation. A thing here is not a thing there. A message takes time to cross distance. An object has properties whether or not we look. The world feels like a collection of definite things arranged in space. Quantum entanglement says, be careful. At the smallest scales, the world may not be assembled that way. The pair may come before the parts. The relationship may be real. The outcome may not be fixed until measurement. And the correlations may be stronger than any ordinary hidden instruction story can explain. Einstein resisted because he saw what was at stake. He was protecting a vision of reality. Bohr defended quantum mechanics because he saw that experiments had already forced the old vision to change. Neither could simply return to the past. The quantum world had opened. The question was how deeply it changed reality. The EPR paradox became a kind of mirror. It reflected the assumptions physicists carried into nature. Do we assume that every measurable property exists before measurement? Do we assume that distant systems always have independent realities? Do we assume that probability means ignorance? Do we assume that the whole is always reducible to its parts? Quantum mechanics challenged each assumption. Entanglement challenged them together. A pair of particles in one shared state does not fit neatly into the classical picture. If you insist that each particle had all its answers from the beginning, experiments will later demand a price. If you accept the quantum state as complete, you must accept that the whole system can possess a reality not divided into separate local pieces. Neither path feels ordinary. That is why the debate endured. Einstein's phrase, spooky action at a distance, remains powerful because it names the discomfort. But it can also mislead if taken too literally. Entanglement is not a force reaching across space. It is not a controllable influence. It does not let one experimenter send a message instantly to another. It is subtler than action in the ordinary sense. It is a correlation rooted in the shared quantum state, a pattern that appears only when results are compared. A sign that the classical idea of pre-existing local properties is incomplete. The spookiness is not that a ghostly signal travels. The spookiness is that the old picture of independent things seems unable to explain the whole pattern. That is much deeper and much quieter. The universe is not shouting, it is whispering through statistics. One measurement gives a random outcome, another measurement gives a random outcome. But thousands of measurements compared carefully reveal a pattern no classical local story can match. The whisper becomes undeniable only through repetition, through patience, through experiment, through mathematics. Einstein's problem would eventually move from argument to test because of this statistical nature. A single pair of particles does not settle the question. But many pairs, measured in different ways, can reveal whether the world follows classical limits or quantum predictions. This is where Bell enters later. But Bell could only enter because Einstein, Podolsky, and Rosen had sharpened the problem. They had asked whether quantum mechanics was complete. They had drawn attention to distant correlations. They had made locality and realism central. They had turned discomfort into a formal challenge. It is one of the beautiful patterns of science that even objections can become foundations. A criticism can become a doorway. A refusal to accept an answer can lead to a deeper answer. Einstein did not end entanglement by objecting to it. He helped reveal its importance. The mystery he resisted became one of the most experimentally tested features of quantum physics. And the story of that testing begins with a question he left behind. Can the world be explained by hidden instructions carried locally by particles? Can the apparent randomness of quantum mechanics be only a mask? Can entanglement be understood without giving up the old idea that distant things are fully separate? For years, these questions hovered. The laboratories were not yet ready. The theorem had not yet been written. The experiments had not yet spoken clearly, but the stage was set. Two particles, one shared quantum state, a distant measurement, a correlated result, Einstein's unease, Bohr's reply, a universe waiting to be tested. In the end, the debate between Einstein and quantum mechanics is not a story of failure. It is a story of seriousness. Einstein took reality seriously enough to demand more from a theory than successful prediction. Bohr took quantum phenomena seriously enough to let go of familiar pictures when experiments required it. Between them, physics became sharper. The question became deeper, and entanglement moved from an odd mathematical feature to a central mystery about the nature of the world. The ordinary universe still appears calm. The moon crosses the night sky. Stars shine with ancient light. A stone rests where it falls. A clock ticks forward. But beneath that calmness lies the unresolved depth that Einstein saw. The world of atoms is not merely a smaller copy of the world of stones. It has its own logic, its own silence, its own strange relationships. And somewhere inside that silence, two particles can be described as one, not because they are close, not because they exchange a message, not because we simply lack ordinary knowledge, but because the quantum state itself refuses to divide them in the way the classical mind expects. Einstein looked at that refusal and asked whether something was missing. Bohr looked at it and asked whether the old expectations were the thing that had to be left behind. The next great step would come from a physicist who found a way to turn this philosophical tension into a measurable test. A way to ask nature directly whether hidden local instructions could explain the quantum world. A way to transform the debate from words into numbers. A way to see whether Einstein's deeper reality could survive. Until then, the question remained suspended, like two particles moving apart into the dark, carrying with them one of the deepest puzzles the universe has ever given us. For many years, the mystery waited in a quiet place between physics and philosophy. Quantum mechanics worked with astonishing precision. It explained the colors of atoms, the behavior of light, the structure of matter, the way electrons arrange themselves around nuclei, the way particles interact, and the way stars shine in the darkness. It helped build the modern world, from lasers and electronics to medical instruments and the hidden circuits inside countless devices. The theory was not weak. It was one of the most successful descriptions of nature ever created. And yet, deep inside it, there remained a question that refused to fade. Was quantum mechanics complete? Was nature truly probabilistic at its deepest level? Were entangled particles really described by one shared quantum state, even when separated by great distance? Or were there deeper hidden facts beneath the surface, unknown variables that carried definite answers all along? Einstein had sharpened the question. Bohr had defended the quantum view. The EPR argument had revealed a deep tension between locality, realism, and the predictions of quantum mechanics. But for a long time, the tension seemed impossible to settle by experiment. It seemed like a question about interpretation, about how one should speak of the theory rather than a question nature could answer directly. Many physicists moved forward. They used quantum mechanics because it worked. They calculated, predicted, designed, and discovered. Atomic physics grew, nuclear physics grew, particle physics grew, solid-state physics grew. Technologies emerged from quantum rules, even while the deeper meaning of those rules remained unsettled. The philosophical unease stayed in the background. Then came John Bell. Bell was not satisfied with leaving the question in a mist of words. He wanted clarity. He wanted to know whether the difference between Einstein's hoped-for deeper local reality and ordinary quantum mechanics could become measurable. Could the debate be turned into a test? Could the universe be asked, not in language, but in numbers? This was the great step. Bell realized that the question was not only philosophical. If particles carried hidden local instructions, then the results of certain measurements would have to obey limits. If quantum mechanics was right, the results could pass beyond those limits. The difference was not a matter of taste or interpretation. It was a difference in the patterns that experiments should reveal. In 1964, Bell published the theorem that changed the story. He showed that no theory based on simple, local hidden variables could reproduce all the predictions of quantum mechanics. This was profound. It meant that Einstein's preferred kind of deeper explanation, one in which particles carried pre-existing local instructions and no influence, traveled faster than light, was not merely difficult to find. It faced a mathematical boundary. If nature obeyed such a local, hidden, variable picture, then certain correlations between measurements could never exceed a certain strength. Quantum mechanics predicted that entangled particles could exceed that strength. So the question became experimental. Would nature obey Bell's limits, or would it follow the stranger quantum pattern? To understand the idea without equations, return to two particles created together and sent far apart. They are entangled. One travels to one detector, the other travels to another. At each detector, a scientist can choose how to measure the particle. The chosen measurement might be imagined as a direction, an angle, or a filter, depending on the experiment. Each measurement gives one of a few possible outcomes, perhaps up or down, perhaps pass or fail, perhaps one click or another. Each result by itself looks random. But when the results from both sides are compared later, patterns appear. The question is, what kind of patterns are possible if each particle carried hidden instructions from the beginning? Suppose, in a classical hidden instruction picture, the particles leave the source with a plan. The plan tells each particle how to respond to any possible measurement it might meet. If measured one way, give one answer. If measured another way, give another answer. The particles may be strongly coordinated because they were created together. But once they separate, each particle can only use the information it carries locally. No instant message, no faster-than-light influence, no secret conversation after separation. Only instructions from the shared past. This is close to the kind of picture Einstein hoped might lie beneath quantum mechanics. The quantum results might look random only because we do not know the deeper instructions. The particles might appear mysteriously correlated only because they had carried matching hidden information all along. But Bell showed that this picture has limits. If particles carry pre-written local answers, then the correlations between their results must satisfy certain inequalities. These are now called Bell inequalities. They are not about only one specific hidden variable model. They are broad constraints. They describe the maximum strength of correlation possible if local hidden instructions are the whole story. Quantum mechanics predicts something stronger. For certain entangled states and certain measurement choices, quantum mechanics predicts correlations that break Bell's inequalities. This is the strange heart of Bell's theorem. The universe could not keep all the old comforts at once. It could not give the full predictions of quantum mechanics while also being explained by local hidden variables in the simple classical sense. Something had to give. Either the quantum predictions would fail in experiment, or the local hidden variable picture would fail. Bell had found a way to make the universe choose. The beauty of Bell's idea is that it does not require us to see hidden variables directly. It does not require us to know what they are. It says that if they exist in a local way, then the results must stay within a certain range. If experiments go beyond that range, then no local hidden variable theory of that kind can explain what is happening. Bell turned a philosophical shadow into a measurable line. On one side of the line stood local hidden instructions. On the other stood quantum entanglement. The experiments would decide which pattern appeared. It is easy to miss how radical this was. Before Bell, one might think that different interpretations of quantum mechanics were all equally beyond experiment. Perhaps one physicist could believe in hidden variables, another could believe in wave function collapse, another could take a more practical view and refuse to discuss what reality was doing between measurements. The laboratory, it seemed, might remain silent. Bell showed that the laboratory did not have to remain silent. Some ideas made different claims about possible correlations, and correlations can be measured. The universe could answer through statistics. A single pair of particles would not be enough. Each individual measurement gives a result that seems random. But repeat the experiment again and again. Prepare many pairs of entangled particles. Measure them with different settings. Compare the results. Count how often the outcomes match, how often they differ, and how those patterns depend on the chosen settings. Over many trials, the hidden order becomes visible. Not in one dramatic flash, not in one single particle, but in the slow gathering of results. Bell's theorem listens to the universe as one might listen to rain in the dark. One drop tells little. Many drops reveal the pattern. The central issue is not whether two particles can be correlated. Classical systems can be correlated too. If two fragments fly apart from an explosion, their motion may be linked. If two cards are drawn from a deck and sent to distant people, one person's card tells something about the other. If two clocks are synchronized and separated, they can show related times. Correlation alone is not strange. The question is, what strength and form of correlation is possible? Entanglement produces correlations that depend on measurement settings in a way no local hidden instruction system can fully imitate. This is subtle. It is not simply that the particles always give the same result. Depending on how the measurements are chosen, the results may agree often, disagree often, or show partial correlations. Quantum mechanics predicts a smooth pattern of correlations as the relative measurement settings change. A local hidden variable model can mimic some of that pattern, but not all of it. Bell found the boundary. Quantum mechanics crosses it. This is why Bell's theorem is one of the deepest discoveries in the foundations of physics. It is not a new planet, a new particle, or a new force. It is a theorem about the structure of reality. It tells us that the world cannot be explained by a certain kind of intuitive local realism if quantum predictions are correct. Locality says that distant events cannot instantly influence one another in a way that sends physical effects faster than light. Realism says that measurement outcomes reflect properties that were already determined by the physical state of the systems, whether or not anyone measured them. Bell showed that the combination in the form of local hidden variables conflicts with quantum mechanics. This does not mean every possible hidden variable theory is impossible. Some hidden variable theories are non-local. They allow a deeper connection that does not fit Einstein's preferred locality. Bell did not erase every possible deeper theory. Instead, he showed that if deeper variables exist, they cannot preserve the simple local picture Einstein wanted. That distinction matters. The lesson is not merely that hidden variables are impossible. The lesson is that local hidden variables cannot reproduce the full quantum pattern. The universe may still have a deeper structure, but it cannot be the comfortable classical structure many had hoped for. Bell's theorem places a quiet pressure on intuition. If we want locality in the strict classical sense, we may have to give up the idea that measurement outcomes were determined in advance for all possible settings. If we want definite hidden properties, we may have to accept some form of non-locality or another departure from ordinary assumptions. If we accept standard quantum mechanics, we accept that entangled systems have correlations that are not reducible to local pre-written answers. No option restores the simple world completely. The everyday world remains useful. Stones still lie where they lie. Planets still orbit. Messages still do not outrun light. But beneath that world, the quantum foundations are not classical. Bell made that unavoidable. Imagine two distant experimenters in two quiet laboratories. A source between them sends one particle to each side. The particles are entangled. Each experimenter can choose between different ways of measuring their particle. The choices are made independently. Each detector flashes one of two possible results. The experiment is repeated again and again. Each time, the source sends a new entangled pair. Each time, the measurement settings may change. Each time, the results are recorded. After many repetitions, the records are brought together. The experimenters compare which settings were used and which outcomes occurred. They search for the pattern. If the particles carried local hidden instructions, the pattern must satisfy Bell's inequality. If quantum mechanics is right, the pattern can violate it. The result is not found in any single measurement. It appears in the relationship among many measurements. That is part of the quiet mystery. Quantum entanglement does not shout across space. It leaves a statistical signature. The particles do not send a message saying that one has been measured and the other must now change. That would be too simple, and it would allow faster than light signaling, which entanglement does not do. Instead, each side sees randomness. Only later, when the records meet through ordinary communication, does the deeper order appear. Randomness locally, correlation globally. Each particle gives an unpredictable result. Together, the pair reveals a pattern. The whole has order that the separate observations hide. This was not the kind of order Einstein wanted. He wanted individual systems to have definite properties beneath the probabilities. But Bell showed that if such properties are local and pre-existing in the classical way, they cannot explain the full set of quantum correlations. The world could be ordered, but not in the old way. Bell himself cared deeply about the meaning of quantum mechanics. He was not content with vague language. He wanted the theory to be clear about what exists and what happens. His work was sharp because it did not hide behind interpretation. It produced a testable inequality. It brought the debate down to measurable correlations. This is one reason Bell's theorem feels so powerful. It is philosophical in origin, mathematical in form, and experimental in consequence. It begins with a question about reality. It becomes a theorem. It ends in laboratories. The theorem also reveals how dangerous it can be to trust intuition too strongly. The assumptions behind local hidden variables feel natural because they match everyday experience. Objects have properties. Separation matters. Causes travel locally. Ignorance produces probability. These ideas are not foolish. They work well in the ordinary world. But the quantum world is not the ordinary world made smaller. It follows a different structure. The mistake is not using intuition. Intuition helps us begin. The mistake is demanding that nature obey intuition at every scale. Bell's theorem is a place where intuition meets its boundary. The boundary is not chaos. It is a new kind of law. To understand the depth of Bell's theorem, it helps to say what it does not say. It does not say that anything can influence anything else instantly in a way we can use. It does not say that information travels faster than light. It does not say that relativity is simply wrong. It does not say that human consciousness creates reality. It does not say that all things in the universe are magically connected in a vague sense. It says something more precise and more unsettling. The correlations predicted by quantum mechanics and observed in entanglement experiments cannot be explained by any theory in which measurement outcomes are determined by local hidden variables carried by each particle from the beginning. That is the clean statement. Inside that clean statement is a deep change in worldview. The old picture imagines that each particle travels with a private set of answers. Bell asks nature whether such private local answer sheets can exist. Quantum mechanics says no. Experiments say the quantum prediction is right. But before the experiments gave their strongest answers, there was the challenge of actually performing them. Bell's theorem opened the door, but the door led into difficult territory. It is one thing to write a theorem. It is another to create entangled particles, send them to separate detectors, choose measurement settings, detect outcomes efficiently, and rule out alternative explanations. The tests had to be delicate. They had to produce pairs of particles in entangled states. They had to measure them in different settings. They had to gather enough data to compare with Bell inequalities. And they had to account for loopholes. A loophole is a way that a local hidden variable explanation might still survive because the experiment was not perfect. Perhaps the detectors missed too many particles. Perhaps the measurement settings were not chosen independently enough. Perhaps some signal could have traveled between the detectors if the measurements were not sufficiently separated in space and time. Perhaps the sample of detected particles did not represent the whole. These loopholes mattered because the question was so fundamental. If an experiment appeared to violate Bell's inequality, one had to ask whether the violation truly came from nature or from some imperfection in the test. This would become a major theme in the experimental history of entanglement. But Bell's theorem itself did not wait for perfect technology to be important. Its importance was immediate to anyone who understood it. It showed that the debate had teeth. It showed that Einstein's question could become a laboratory question. It showed that philosophy, when sharpened enough, could turn into physics. In a way, Bell completed the transformation that EPR began. EPR asked whether quantum mechanics was complete. Bell asked what the world would look like if it were completed locally. Then he showed that such a local completion would make predictions different from quantum mechanics. The rest was up to experiment. There is a calm beauty in the logic. Start with two particles. Assume they carry hidden local instructions. Assume no faster than light influence. Derive a limit on correlations. Compare with quantum mechanics. Then compare with nature. Few arguments in physics move so quietly and strike so deeply. The spirit of the theorem can be felt without equations. If the world is made of separate local pieces carrying fixed instructions, then there are only so many ways their answers can line up across many possible questions. Quantum mechanics predicts that entangled particles line up too well in a pattern too subtle and too strong for those instructions. So either the answers were not fixed in that local way, or separateness is not as simple as it seems, or one of the other assumptions behind the test must fail. Reality cannot be the old picture. This is what Bell revealed, not with a telescope, not with a particle accelerator, not with a newly discovered material, but with a theorem about possible worlds. Some discoveries reveal things in space, planets, moons, galaxies, nebulae. Others reveal things in matter, electrons, nuclei, quarks, neutrinos. Bell's theorem revealed something about the logical structure of physical reality. It told us that certain worlds we can imagine are not compatible with quantum predictions. It narrowed the possible shape of truth. And when experiments later confirmed the quantum violations, it narrowed that shape further. The theorem also changed the status of entanglement. What had once seemed like an odd feature of the equations, or a troubling thought experiment, became experimentally meaningful. Entanglement was no longer only spooky language in a debate. It was the source of correlations that could be tested against classical bounds. This helped begin the long transformation of entanglement from philosophical puzzle into physical resource. Today, entanglement sits at the heart of quantum information science. But that later technological future depends on the foundational recognition that entanglement is real, measurable, and unlike classical correlation. Bell helped make that recognition unavoidable. Imagine for a moment that the experiments had gone the other way. Imagine the Bell tests had obeyed the classical limits and failed to show quantum violations. That would have been a crisis for quantum mechanics. It would have suggested that the theory's predictions were wrong for entangled systems. It might have opened the door to a local hidden variable completion. Einstein's instincts might have been vindicated in a strong way. But that is not what happened. Again and again, experiments found the quantum pattern. Still, before the experiments spoke with increasing strength, there was a suspenseful quiet. Bell had written the test. The universe had not yet been asked with enough precision. The old debate had become a question that laboratories could ask. The mystery had become measurable. The EPR argument had said that if quantum mechanics is complete, something strange is happening with distant systems, or else the theory is missing something. Bell said, "Let us see what any local missing something would require." Then he found the inequality. This inequality is not merely a mathematical line, it is a boundary around the classical imagination. Inside it live the worlds where particles carry local instructions and correlations never exceed the allowed limit. Outside it lies the quantum world, where entangled particles produce patterns that cannot be explained that way. Nature, we now know, chooses the outside. But Bell's theorem gave us the map. The old dream was not foolish, it was beautiful. A universe of local causes and definite properties is elegant. It gives the mind a kind of peace. Everything has its state. Everything moves according to hidden detail. Probability is only ignorance. Distance protects independence. The whole is built from separate pieces. Bell did not destroy that dream with rhetoric. He tested its consequences. That is why the result is so strong. Science is most powerful when it does not merely say an idea feels wrong, but shows what the idea would imply and then asks whether the implication holds. Local hidden variables imply Bell inequalities. Entangled quantum mechanics violates them. Nature can be asked. The asking itself required care. The measurement settings must be varied, the particles must be separated, the detections must be recorded, the statistics must be analyzed, the experimenters must make sure that the pattern is not an artifact. Over time, stronger and stronger experiments would close more loopholes. But already, with Bell, the philosophical fog had changed. It was no longer enough to say that perhaps the particles simply carried hidden instructions. One had to ask whether those instructions could reproduce the Bell test correlations. If they are local, the answer is no. This no is one of the quietest revolutions in physics. It does not change how a falling apple looks. It does not alter the orbit of the moon. It does not make everyday objects behave strangely, but it changes the foundation beneath them. It tells us that the classical idea of a world assembled from independent local properties cannot be the full story. The visible calm remains. The hidden structure changes. There is a useful way to think about this. In classical physics, the state of a whole system is usually built from the states of its separate pieces. If you know the state of each piece, you know the state of the whole. A clock is made of gears. A gas is made of molecules. A solar system is made of planets and the sun. The whole can be complicated, but in principle it is assembled from pieces with their own properties. In quantum mechanics, entangled systems reverse this expectation. The whole can have a definite state, while the individual systems do not have definite states of their own in the same way. The whole is not merely a summary of the pieces. The whole may be the more complete description. Bell's theorem shows that this is not only poetic language. It has measurable consequences. If you try to force the entangled whole back into independent local pieces with pre-existing answers, you lose the quantum correlations. The universe keeps the whole. The pieces alone are not enough. This may be one of the deepest lessons of entanglement. At small scales, reality can be relational in a way classical physics did not expect. Not relational in the vague sense that everything affects everything, but relational in the precise sense that the quantum state of a composite system may not divide into separate states for each component. The relationship has physical content. Bell made the content testable. There is also an important subtlety in the word measurement. In Bell tests, the choice of measurement setting matters. If one measures spin along one direction, one asks one kind of question. If one measures along another direction, one asks another. Quantum mechanics does not say that the particle carries definite answers to all possible questions simultaneously in the classical way. The act of measurement selects a context, and the outcome appears within that context. Local hidden variable theories, by contrast, would need the particle to have answers ready for all relevant settings, or at least a hidden mechanism that produces them locally. Bell's inequalities arise because those possible answers must be mutually consistent across different choices. Quantum mechanics violates that consistency, not randomly, precisely. It predicts a pattern that no table of local pre-written answers can match. This is why simple analogies eventually fail. Globes in boxes cannot violate Bell inequalities. Cards in envelopes cannot. Prearranged signals cannot. Classical tricks can create strong correlations, but they cannot reproduce the full quantum pattern under the conditions Bell described. Entanglement is not ignorance about which glove is where. It is not merely missing information about a classical state. It is a different kind of state. The quantum state of the pair contains possibilities that are not reducible to separate hidden properties. When physicists say entanglement is non-classical, this is what they mean. It is not just strange, it exceeds the classical limits. Bell gave those limits a form. The later experiments measured the excess. The theorem also has a quiet relationship with freedom of choice, or more carefully, measurement independence. To test Bell inequalities, one assumes that the choices of measurement settings are not secretly correlated with the hidden variables of the particles in a conspiratorial way. If everything, including the experimenter's choices, was somehow prearranged in just the right way, one could evade the conclusion. This possibility is often called superdeterminism. It is logically possible in a broad sense, but it requires a deep and unusual correlation between the measuring devices and the particles that most physicists do not consider a natural explanation. This shows that Bell's theorem rests on assumptions, as all physical arguments do. But the assumptions are not arbitrary. They capture the ordinary idea that experimenters can choose settings independently of the hidden properties of particles emitted from a source, and that no faster-than-light influence carries information between distant measurement events. Under these assumptions, local hidden variables fail. This carefulness matters because quantum entanglement is often surrounded by exaggeration. It is easy to turn it into a vague claim that everything is instantly connected, or that thoughts can affect distant objects, or that physics has proven some mystical unity. Bell's theorem does not say that. Entanglement is precise, delicate, and experimentally defined. Its strangeness is stronger when it is not blurred. The truth is enough. Nature violates Bell inequalities. Entangled particles show correlations that cannot be explained by local hidden variables. No usable faster-than-light signaling occurs. The old classical picture is incomplete. That is already astonishing. The calmness of the result makes it even more powerful. The experimenters do not see lightning between detectors. They do not hear a signal. They do not watch one particle visibly command the other. They see detector clicks. They record settings. They compare data. They find a statistical violation. A quiet table of numbers reveals that reality is not classical. There is a hidden poetry in that. The deepest revolutions are sometimes not loud. They appear as a pattern in results, a deviation from a bound, a curve where a straight line was expected, a correlation too strong for the old world. Bell's theorem was such a revolution. It did not overthrow quantum mechanics. It clarified what quantum mechanics had been saying all along. It revealed that entanglement is not merely a mathematical inconvenience, but a sign that the structure of reality cannot be described by local classical properties. Einstein's challenge had asked for completeness. Bell's answer said that if a completion exists, it cannot be local in Einstein's desired sense. The universe may be complete in the quantum way, or it may have a deeper non-local order, or it may require an interpretation still stranger. But the simple local hidden variable dream is not enough. This does not make Einstein irrelevant. It makes him central. Without his unease, the question might not have been pressed so sharply. Without EPR, Bell might not have found the same path. Einstein's doubt helped expose one of the deepest truths in quantum theory. Science often advances this way. A theory succeeds. A critic asks what it really means. A paradox appears. A theorem sharpens it. An experiment decides. The story of entanglement follows this rhythm beautifully. Quantum mechanics produced the strange state. Einstein challenged its meaning. Bell found the test. Experiments revealed the pattern. The path from philosophy to laboratory is one of the great achievements of modern physics. At this point in the story, the universe stands before the experiment. The theorem has been written. The old assumptions have been placed under pressure. The question has become measurable. Imagine the particles once more. They are born together from a common source. They separate into opposite directions. The detectors wait. The measurement settings are chosen. Each detector records an outcome. The results seem random at each side. But when compared, they build a pattern. If the pattern stays within Bell's boundary, then Einstein's local hidden hope survives. If the pattern crosses the boundary, then the quantum world is stranger than the old picture allowed. The particles fly. The detectors click. The numbers gather. The universe prepares to answer. There is a kind of stillness before such an answer. Not because the laboratory is silent, though it may be. Not because the particles hesitate, because particles do not hesitate in the human sense. But because the meaning is suspended. For decades, physicists had argued about the nature of quantum reality. Now the argument could be placed into apparatus, optics, detectors, settings, and statistics. a philosophical question, had become an experimental ritual. Prepare. Separate, measure, compare, repeat. The repetition matters. Quantum mechanics does not promise certainty for one pair, it promises probabilities across many pairs. Bell's inequality does not ask what one particle will do. It asks what pattern many particles can produce under different measurement choices. The universe speaks through the many. Each individual event may be unpredictable. The collection is lawful. That is quantum mechanics in miniature. Randomness and law together. Chance and structure, uncertainty and precision. The old deterministic worldview expected that precision must come from certainty underneath. Quantum mechanics offers precision without that kind of certainty. It gives exact probabilities, not exact individual outcomes. Bell's theorem shows that trying to restore ordinary certainty locally cannot reproduce what the probabilities predict. This is perhaps the most difficult emotional shift. The universe can be lawful without being deterministic in the old sense. It can be ordered without being classical. It can be precise without giving every event a pre-written local cause. It can preserve the speed limit of light for messages while still producing entangled correlations that defy local hidden variables. Reality is more subtle than any simple phrase. The mystery is not solved by saying everything is random. It is not solved by saying everything is connected. It is not solved by saying hidden variables are impossible in every form. The truth lies in the careful middle. Quantum mechanics predicts non-classical correlations. Bell showed local hidden variables cannot match them. Experiments confirm the violations. No faster than light communication is possible. The meaning remains deep. This is where the question becomes sharp enough to cut. Before Bell, one could hide in interpretation. After Bell, one had to face experiment. The universe could no longer be imagined as classical underneath without paying a price. Either locality, realism, measurement independence, or some other assumption had to be reconsidered. Different interpretations choose different paths. Standard quantum mechanics accepts the quantum state and its probabilistic predictions. Non-local hidden variable theories accept deeper variables but abandon locality. Many worlds' interpretations keep the wave function evolving without collapse, but change the meaning of outcomes. Relational and informational approaches rethink what quantum states describe. Bell's theorem does not force everyone into one interpretation. It forces everyone to respect the same boundary. Any interpretation must account for Bell inequality violations. Any serious picture of reality must explain why entangled particles behave as they do. The theorem is a gate through which all interpretations must pass. This is why Bell's work remains so important. It did not end the mystery, it refined it. It did not tell us exactly what reality is. It told us what reality is not a simple local hidden variable machine. Not a world of particles carrying all answers independently from the beginning, sealed off from distant measurement choices while still reproducing the quantum pattern. That world is gone. In its place is something quieter and stranger. A world where entangled systems must be understood as wholes. A world where measurement outcomes do not fit pre-written local tables. A world where the deepest structure of correlation is not classical. The night sky above us still looks unchanged. No constellation rearranges itself because of Bell's theorem. No planet alters its orbit. The moon remains calm. The stars remain distant. But the meaning of matter and light has changed. Every photon belongs to a universe where quantum rules hold. Every atom is built from a theory whose deepest correlations refuse classical explanation. The ordinary world remains, but its foundation is stranger than it appears. This is often how science changes us. Not by changing what we see first, but by changing what we understand beneath what we see. The stone is still a stone. The star is still a star. But now the stone's atoms and the star's light belong to a reality in which entanglement is possible. Bell inequalities can be violated, and the whole may not reduce to separate local pieces. The world is familiar on the surface, unfamiliar underneath. Bell's theorem is one of the bridges between those layers. It leads from the familiar desire for local reality into the hidden architecture of quantum correlations. It tells us that the deepest world is not a clockwork of little objects carrying fixed answers through space. It is something else, something described by quantum states, something capable of shared properties across distance, something that gives random results locally and precise correlations globally. Something that Einstein suspected could not be the final word, and that Bell showed could not be replaced by the simplest alternative. As the story moves forward, the next step belongs to the experimenters, to John Clauser, to Alain Aspect, to Anton Zeilinger, to later teams who closed loopholes with greater and greater care, to photons traveling through optical paths, to detectors waiting in darkness, to choices made quickly, to correlations counted patiently, to the Nobel Prize that recognized how a philosophical puzzle became a foundation for quantum information science. But before the apparatus begins, we can remain with Bell's quiet insight. If particles carry local hidden instructions, their correlations must stay within a boundary. If quantum mechanics is right, entangled particles can cross it. Nature was asked. And nature, with extraordinary consistency, chose the quantum world. The old dream did not vanish in noise. It faded through numbers, through inequalities, through the repeated click of detectors, through patterns too strong for local hidden variables, through the realization that reality is not assembled in the simple way our senses suggest. Two particles drift apart, two detectors wait, the settings are chosen, the results appear. And in the comparison hidden beneath randomness, the universe reveals a deeper order, not the order Einstein hoped for, not the order everyday life teaches, but an order all the same. A quantum order, quiet, precise, unsettling, and real. The question had become sharp enough for the laboratory. For decades, quantum entanglement had lived partly in thought experiments, partly in equations, and partly in the philosophical tension between Einstein and Bohr. It was a strange possibility in the formalism of quantum mechanics, a feature that seemed to bind two distant systems into one shared description. It had troubled Einstein because it appeared to challenge the old idea of a world made from separate local realities. It had inspired Bell because it seemed possible that the mystery could be tested. Now the question moved from paper into apparatus, from argument into experiment, from what might be true to what nature would actually do. The experimenters did not need to look for dramatic flashes across space. They did not expect to see one particle visibly reach for another. The mystery of entanglement is not theatrical in that way. It hides in correlations. It appears only after many measurements, many repeated trials, many careful comparisons between results that seem random when viewed alone. The work required patience. A source had to create pairs of quantum particles. The particles had to be entangled. They had to travel in different directions. Their properties had to be measured in carefully chosen ways. The results had to be recorded. Then, after many pairs had been measured, the records had to be compared. If Einstein's preferred local, hidden variable picture was right, the correlations would stay within Bell's limits. If quantum mechanics was right, the correlations could violate those limits. The detectors would not announce the meaning. They would only click. One event, then another, then thousands more. Only later, in the gathered pattern, would the answer appear. This is one of the quietest dramas in science. A question about the nature of reality, carried by tiny particles of light, answered by statistics. The first great tests were not perfect. No experiment ever begins perfect. Instruments have limits. Detectors miss particles. Sources are not ideal. Settings take time to change. Background noise enters. Photons are lost. Measurements must be interpreted carefully. But the early tests mattered because they took Bell's theorem out of the realm of possibility and placed it in the physical world. One of the important early steps came from John Clauser. Clauser understood that Bell's theorem could be tested with real photons. Along with Stuart Friedman, he performed a pioneering experiment in the early 1970s using pairs of photons emitted by calcium atoms. The photons traveled in different directions, and their polarizations were measured. Polarization describes the orientation of light's electric field, and for photons it can be used as a quantum property in entanglement experiments. The setup was delicate. The idea was profound. If the photons behaved like classical objects carrying local hidden instructions, their measurement correlations should obey Bell-type limits. If they behaved as quantum mechanics predicted, the correlations could go beyond those limits. The experiment found results in agreement with quantum mechanics. It was not the final word. There were still loopholes, but it was a landmark. For the first time, Bell's abstract inequality had been tested in a serious laboratory experiment, and nature had leaned toward the quantum answer. The universe had whispered that Einstein's local hidden hope was in trouble, not with thunder, not with spectacle, with photon pairs, with polarizers, with counters, with numbers. There is something almost strange about how humble the equipment can seem compared with the meaning. A laboratory table, optical components, detectors, wires, recorded counts. And yet the question being asked is whether the universe is made of local, pre-existing properties in the way ordinary intuition suggests. A small experiment can carry an enormous question. Clauser's work showed that the question was real. It could be asked experimentally. It could be measured. It was no longer only a debate between interpretations. But one experiment, especially in such a difficult field, is not enough to settle a foundational question forever. The early tests had limitations, and physicists knew it. The most important limitations came to be known as loopholes. A loophole is not necessarily a flaw that ruins an experiment. It is an opening through which an alternative explanation might still escape. One major issue was the detection loophole. Detectors are not perfect. If many particles are lost or missed, then the particles that are actually detected might not fairly represent all the particles produced. A local hidden variable theory might exploit that imperfection, at least in principle. Perhaps the detected sample shows quantum-like correlations, while the full set would not. Another issue was the locality loophole. If the measurement on one particle is not clearly separated in space and time from the measurement on the other, then a signal traveling at or below the speed of light might somehow pass between the two measurement events. If that were possible, a local explanation could still survive. To close this loophole, the choices of measurement settings and the measurements themselves must happen so quickly and so far apart that no light speed or slower signal can connect them in time. There is also the freedom of choice loophole, sometimes called measurement independence. The measurement settings should be chosen in a way that is not secretly correlated with the hidden properties of the particles. If the universe somehow arranged the settings and the particle properties together from the beginning in just the right way, it could mimic quantum results while preserving a kind of strange determinism. Most physicists do not consider such conspiratorial explanations. Natural but serious experiments try to push even these possibilities farther away. The existence of loopholes did not mean quantum mechanics was wrong. It meant the question was important enough to demand care. The goal was to make experiments tighter, cleaner, more difficult for any local, hidden variable explanation to survive. After Clauser's work came further experiments, and among the most famous were those led by Alain Aspect in the early 1980s. Aspect's experiments improved the tests of Bell's inequalities in crucial ways. He used entangled photons and measured their polarizations, but one of his most important advances involved changing the measurement settings while the photons were already in flight. This mattered because it made it much harder to imagine that the particles had known in advance which measurement they would face, or that some ordinary signal could coordinate the outcomes between the two sides. The setting choices were changed rapidly. The photons traveled apart. The detectors recorded the results. Again, the correlations matched quantum mechanics. Again, Bell inequalities were violated. Again, the old local hidden variable picture weakened. Aspect's work did not close every possible loophole by modern standards, but it was a major step. It showed that even when the measurement settings were varied during the experiment, the quantum correlations persisted. The entangled photons behaved as quantum mechanics said they would. The universe was asked more carefully. It gave the same strange answer. This is the rhythm of the experimental story. Ask the question, tighten the test, remove an escape route, ask again. The answer remains quantum. Over time, the experiments became more refined. New sources of entangled photons were developed. Detectors improved, distances increased, timing became sharper, random setting choices became better. Experiments tested not only photon polarization, but also other physical systems, including atoms, ions, superconducting devices, and solid-state systems. The concept of entanglement moved from rare and delicate demonstration into an entire field of research. One of the central figures in this transformation was Anton Zeilinger. Zeilinger and his collaborators carried entanglement into new territory. They performed experiments with entangled photons, quantum teleportation, entanglement swapping, multi-particle entanglement, and long-distance quantum communication. His work helped show that entanglement was not only a philosophical puzzle. It could be manipulated, transmitted, used, and studied as a resource. Quantum teleportation is one of the most misunderstood phrases in science, so it must be approached gently. It does not mean teleporting a person. It does not mean moving matter instantly from one place to another. It means transferring an unknown quantum state from one system to another, using a shared entangled state and an ordinary classical message. The original quantum state is not copied. In fact, quantum mechanics forbids perfect copying of an unknown quantum state. Instead, the state is destroyed in one place and reconstructed in another after the necessary classical information arrives. Because that classical information cannot travel faster than light, quantum teleportation does not allow instant communication. Still, it is extraordinary. It shows that entanglement can be used as a kind of channel for quantum information, but only when paired with ordinary communication. It reveals that the information describing a quantum state is not like a simple object being carried through space. It can be transferred through a process that depends on entanglement, measurement, and classical signals. This is part of how entanglement changed from mystery into tool. At first, it seemed like a problem. Then it became a test. Then it became a resource. Clauser helped show that Bell's theorem could be tested. Aspect refined the experimental challenge and strengthened the case. Zeilinger helped turn entanglement into a central pillar of quantum information science. Together, their work formed a bridge from the deepest foundations of quantum theory to the technologies now being explored in quantum communication, quantum cryptography, and quantum computing. In 2022, the Nobel Prize in Physics was awarded to John Clauser, Alain Aspect, and Anton Zeilinger for experiments with entangled photons, the violation of Bell inequalities, and pioneering quantum information science. The award recognized more than a set of technical achievements. It recognized a change in how physics understands entanglement. A puzzle that once seemed almost philosophical had become an experimentally confirmed feature of nature and a foundation for new technologies. The strange link between particles had become real enough to build with. Still, the story of testing entanglement did not end with the early experiments or even with the Nobel Prize. The drive to close loopholes continued for decades. Physicists wanted tests so strong that no reasonable local hidden variable explanation could remain. They wanted high detection efficiency so that missed particles could not explain the result. They wanted large separation and fast setting choices so that no light speed signal could coordinate the measurements. They wanted careful randomness in setting selection. They wanted clean statistics. They wanted different physical systems to give the same answer. In 2015, several landmark experiments reported loophole-free Bell tests, or tests that closed the major loopholes at the same time under standard assumptions. Some used entangled electron spins in diamond defects separated by distance. Others used entangled photons with improved detectors and fast random choices. These experiments were different in design, but they pointed in the same direction. Bell inequalities were violated. The quantum predictions held. Local hidden variables, in the simple Einstein-like sense, were ruled out with unprecedented strength. The old escape routes became narrower. It is important to say this carefully. Physics rarely closes every imaginable loophole in an absolute philosophical sense. One can always invent extreme possibilities, such as a universe where all measurement choices and particle properties were correlated from the distant past in a vast conspiracy. But science works by testing natural, physically meaningful explanations. And by that standard, the modern Bell experiments are extraordinarily strong. The result is clear. Nature does not behave like a local hidden variable machine. Entanglement is real. Its correlations are non-classical, and yet no faster than light messaging is possible. This combination remains one of the most subtle truths in physics. The experiments do not show that one can send a chosen message instantly across space. They do not show that one observer can control the other observer's outcome. Each side sees random results. The magic, if one wants to call it that, appears only when the two records are later compared. The comparison must happen through ordinary communication, a phone call, a cable, a light signal, a physical message, limited by the speed of light. Only then do the correlations reveal themselves. This is why entanglement can coexist with relativity. It challenges the classical idea of separability, but it does not let signals outrun light. It reshapes our concept of reality without breaking the causal order of usable communication. Einstein's relativity remains. Quantum entanglement remains. The universe holds both, and the attempt to understand how they fit together continues. There is a quiet wonder in the experimental details. Photons are often used because they travel easily and interact weakly with their surroundings. They can move through optical fibers or through open air. Their polarization can be measured with polarizers and detectors. Pairs of entangled photons can be created in special crystals using a process called spontaneous parametric down conversion, where one photon entering a crystal can produce two lower energy photons whose properties are linked. The crystals sit in the path of laser light. The paired photons emerge. They travel down different arms of the experiment. Their polarizations are measured at chosen angles. The detectors click. The data accumulates. What seems like a quiet optical experiment becomes a test of local reality. In other experiments, entanglement is created between trapped ions, atoms, superconducting circuits, or defects in diamonds. Each platform has strengths and weaknesses. Photons are excellent for distance, but can be lost. Matter-based systems can be easier to store and detect, but harder to separate over large distances. Quantum information science now studies how to combine these strengths, creating networks where quantum states can be generated, stored, transmitted, and measured. All of this grows from the same root: entanglement, the shared quantum state that cannot be reduced to independent parts, the state that disturbed Einstein, the state Bell made testable, the state experiments confirmed, the state modern technologies now try to use. The experimental story also teaches humility. Nature does not reveal its foundations easily. The first Bell test did not end the debate in a single stroke. They opened a path. Each generation of experiments improved the question. The detectors became better. The distances became larger. The random choices became faster. The assumptions became clearer. The loopholes narrowed. Science moved not by one proclamation, but by repeated refinement. This is how certainty grows in physics. Not as absolute certainty beyond all imagination, but as a thickening web of evidence. Different experiments, different systems, different methods, all pointing to the same conclusion. Entangled particles violate Bell inequalities. Quantum mechanics predicts the pattern. Nature follows the pattern. The old local hidden variable picture fails. This evidence does not remove all mystery. In some ways, it deepens it. Before the experiments, one could hope that quantum mechanics was only incomplete in a familiar way. Perhaps hidden instructions would restore the old order. Perhaps particles had definite answers all along, and our theory was only statistical because we did not know enough. After Bell tests, that hope becomes much harder. If hidden variables exist, they must be stranger than the old classical idea. They must be non-local or depend on unusual assumptions or belong to an interpretation that changes other parts of the picture. The easy escape is gone. The universe did not return to classical comfort. It chose the quantum pattern. And this choice was not made in metaphor, it was made in laboratories, through photons, through atoms, through detectors, through numbers, through experiments repeated across decades. One can imagine the long arc of the story as a slow conversation with nature. Einstein asks whether the quantum world is complete. Bohr answers that the old classical demands may no longer apply. Bell asks what local hidden variables would actually predict. Clauser asks the photons. Aspect asks them again with changing settings. Zeilinger asks what entanglement can do. Later experiments ask with greater distance, sharper timing, and better detection. And again, nature answers in correlations. The answer is not simple. It does not say everything is connected in an ordinary way. It does not say distance is meaningless. It does not say messages travel instantly. It says something quieter. When two systems are entangled, the whole cannot always be understood as two separate systems carrying definite local properties. Their measurement outcomes, though random alone, display correlations that exceed the limits of local hidden variable theories. That is the answer. Careful, precise, strange. The more one sits with it, the more profound it becomes. The experimenters did not merely test a mathematical inequality, they tested an image of reality. They tested whether the world beneath appearances could still be imagined as a collection of separate little objects with properties written inside them from the beginning. The answer was no, not in that simple way. Reality is not less real. It is not less lawful. But it is not classical at its roots. This is why the experiments changed physics. They did not make quantum mechanics useful. It was already useful. They did not invent entanglement. It was already in the theory. They did not overthrow relativity. Usable signals still obey the speed of light. They showed that the strange feature Einstein disliked is not merely a defect in our understanding. It is a real, testable feature of the world. And then they helped transform that feature into a new science of information. Quantum information begins from a simple shift. Information is physical. Information is not only an abstract thing in books or minds, it is stored in states of physical systems. Classical information can be stored in bits with values like 0 or 1. Quantum information can be stored in quantum bits or qubits, which can exist in superpositions and become entangled with one another. A qubit is not merely a smaller bit, it follows quantum rules. When qubits become entangled, the state of the whole system can contain relationships that are not present in the parts alone. This is one reason quantum computers may be able to solve certain problems differently from classical computers. It is not because they simply try every answer in a magical parallel way, as is sometimes said too loosely. The real power comes from carefully arranged superposition, interference, and entanglement, allowing some computational paths to reinforce and others to cancel. Quantum computers are still developing. They are not magical machines that instantly solve every problem. But for certain tasks, especially those involving quantum systems themselves, optimization, simulation, or mathematical structures, they may offer powerful new approaches. Entanglement is central to that possibility. Quantum cryptography also uses quantum principles to protect information. In certain protocols, attempts to eavesdrop on a quantum communication channel disturb the quantum states in detectable ways. Entanglement can be used in related security schemes, where correlations help reveal whether a channel has been compromised. Quantum communication imagines networks where entanglement can be distributed between distant nodes. Such networks could connect quantum computers, sensors, and secure communication systems. To build them, physicists must learn to generate entanglement reliably, transmit it over distance, store it in quantum memories, and protect it from noise. The fragile mystery must become engineering. This is one of the great transformations of modern science. A feature once used to question reality itself becomes something engineers try to preserve in a device. Entanglement is delicate, but useful. It can be destroyed by interaction with the environment, but it can also be created, controlled, and measured. It is both philosophical and practical, both strange and technical, both a riddle and a resource. Anton Zeilinger's work helped show this dual nature with great clarity. Experiments in quantum teleportation, long-distance entanglement, and multiparticle quantum states demonstrated that entanglement was not confined to thought experiments. It could be used to move quantum information, connect systems, and explore new forms of communication. Entanglement swapping is especially beautiful. In this process, two particles that have never directly interacted can become entangled through measurements performed on their partners. Imagine two entangled pairs. One particle from each pair is brought together and measured jointly. As a result, the two remaining particles, which may be far apart and may never have met, can become entangled. The relationship is created through the structure of the whole quantum process. Again, this does not allow faster-than-light messaging. Again, the full result requires classical communication. But it reveals how entanglement can be extended, rearranged, and distributed. Entanglement swapping is important for quantum repeaters, devices that may one day help send entanglement over very long distances. Ordinary optical signals weaken as they travel through fibers. Classical repeaters can amplify classical information, but unknown quantum states cannot simply be copied because of the no-cloning theorem. Quantum repeaters would instead use entanglement, swapping, and purification to extend quantum communication across larger networks. The ideas are complex, but the feeling is simple. The strange link between particles is becoming the foundation of a new kind of infrastructure. Not a web of ordinary signals alone, a quantum network. A network where entanglement is distributed like a fragile thread of correlation across space. This brings the story back to distance. Einstein worried about distance. He worried about what it meant for two distant systems to be correlated in the quantum way. Today, scientists send entangled photons across cities, through fibers, between mountaintops, and even in experiments involving satellites and ground stations. The goal is not to send messages faster than light, but to use entanglements correlations for secure communication and quantum information tasks. Distance no longer merely threatens entanglement. Distance becomes a challenge for using it. How far can it be sent? How well can it be preserved? How can noise be reduced? How can the fragile state survive the real world? The philosophical puzzle becomes a technological frontier, yet even as technology develops, the old mystery remains. What is the quantum state? What does measurement really do? Why does entanglement exist? How does the world we see emerge from the quantum world beneath it? What does it mean for the whole to be more complete than the parts? The experiments answer one question with great force. Local hidden variables cannot explain the observed correlations, but they do not remove the deeper wonder. They make the wonder sharper. The universe has shown us what it is not. It has not fully told us what it is. This is often how fundamental physics progresses. It closes some doors and opens deeper rooms. Bell tests closed the door on simple local hidden variable explanations. Behind that door was not an empty hallway, but a larger mystery, the nature of quantum reality itself. Some interpretations say that measurement causes the wave function to collapse, selecting one outcome from many possibilities. Some say that all outcomes occur in branching worlds, and entanglement describes the structure of those branches. Some say particles have definite positions guided by a non-local pilot wave. Some say quantum states describe information, relations, or expectations rather than ordinary physical objects. The experiments do not settle all of these interpretations, but they constrain them. Any interpretation must respect Bell inequality violations. Any interpretation must explain why entangled systems behave as they do. Any interpretation must accept that the old classical picture is gone. There is a quiet freedom in that, though it may not feel like comfort. The universe is not required to fit the first picture we formed from ordinary life. Ordinary life is a small layer of reality. It is the layer of warm objects, slow speeds, large numbers of particles, and constant environmental interaction. In that layer, things look classical. Cups stay on tables, stones fall, planets orbit, signals travel through air or wires, causes feel local, objects have stable properties. But beneath that layer, in the small and delicate world, nature behaves differently, not chaotically, with superposition, with uncertainty, with measurement, with entanglement, with correlations beyond Bell's bounds. The experiments reveal that the everyday world is not false but emergent. It is a reliable surface built from deeper rules that do not look like the surface itself. A wave can look smooth from far away while being made of countless molecules. A solid table can feel continuous while being mostly empty space and quantum fields. A classical world can arise from quantum foundations. The familiar can grow from the strange. The experiments of Clauser, Aspect, Zeilinger, and later teams help us see the strangeness directly enough to trust it. There is also a human beauty in the story. These were not experiments of brute force. They were experiments of delicacy. They required careful control of light, precise timing, thoughtful design, and a deep respect for possible errors. They required scientists to take a philosophical question seriously enough to build instruments around it. The laboratory became a place where reality was asked whether it was classical, and reality answered no. Imagine a photon leaving a source. It is not bright to the eye. It is one quantum of light. Its partner travels the other way. The two are described by a shared state. They move through optical paths. At the last moment, settings may be chosen. The photons meet polarizers. Detectors wait in darkness. One detector clicks. Another detector clicks. The individual clicks are small, almost nothing. But in the long record, they become a message from nature. Not a message sent by one photon to the other. A message to us. a pattern saying that the old local hidden picture cannot hold. That is the kind of mystery entanglement gives. It is not noisy. It is not theatrical. It is quiet enough to be missed unless one knows how to listen. The universe often speaks this way. The cosmic microwave background is a faint microwave glow, yet it reveals the early universe. Gravitational waves are tiny ripples in space-time, yet they reveal merging black holes. Spectral lines are narrow colors in light, yet they reveal the chemistry of stars. Bell violations are statistical patterns in detector clicks, yet they reveal that reality is not classical at its roots. The deepest signals are sometimes faint. The meaning is enormous. As experiments became more precise, entanglement became less like a paradox and more like a fact of life in quantum physics. It entered textbooks, laboratories, technologies, and new theories. It became a quantity that could be measured and manipulated. Physicists developed ways to describe how much entanglement a system has, how it changes, how it spreads, how it can be protected, and how it can be used. This is another transformation. A mystery becomes measurable. A measurable feature becomes a resource. A resource becomes technology, but its origin remains mysterious enough to keep returning us to the beginning. Why does the universe allow wholes that cannot be reduced to parts? Why does measurement reveal correlations beyond classical limits? Why is no faster than light communication possible, even though the correlations ignore the old local hidden variable explanation? Why do quantum rules produce the familiar world when many particles interact? The answers are not finished. Physics continues. But the experimental verdict on Bell's question is among the clearest results in modern science. Local hidden variables cannot explain entanglement. The quantum world is real, and it is not classical. This realization changed the emotional landscape of physics. Before, quantum mechanics could be treated as a calculation tool, strange but practical. After Bell experiments, entanglement became a window into the structure of reality. It showed that the difference between quantum and classical was not only a matter of scale or ignorance. It was a difference in the possible patterns of the world. Classical nature has one set of limits. Quantum nature exceeds them, not in every way, not in a way that permits anything imaginable, but in a precise, experimentally verified way. That precision is what keeps the mystery from becoming vague. The universe is not saying that all boundaries vanish. It is saying that one boundary, drawn by local hidden variables, is crossed. The speed of light remains a boundary for signals. The uncertainty principle remains a boundary for certain pairs of knowledge. The no-cloning theorem remains a boundary for copying quantum states. Quantum mechanics is full of boundaries, but they are not the old boundaries. Reality has structure. The structure is simply stranger than classical intuition expected. This is why Bell tests are so important for understanding entanglement. Without them, entanglement might be described as merely an odd mathematical correlation. With them, it becomes a tested distinction between possible worlds. A classical world with local hidden instructions would produce one pattern. The quantum world produces another. We live in the quantum world. The experiments do not require us to abandon reason. They require us to refine it. Reason led from EPR to Bell. Reason designed the experiments. Reason analyzed the data. Reason rejected the old picture because the evidence demanded it. Quantum mechanics is not a defeat of rationality. It is rationality discovering that nature is deeper than common sense. Common sense is local, classical, and human-sized. Physics must be larger. It must include the very small, the very fast, the very massive, the very distant, and the very strange. Entanglement belongs to that larger physics. The story of its experiments is therefore a story of trust. Trusting the mathematics enough to test it, trusting the instruments enough to listen. trusting the data enough to change a worldview, trusting that if nature speaks against intuition, intuition must bend. Einstein's intuition was profound, but even profound intuition can meet its edge. Bohr's defense of quantum mechanics was deep, but Bell's theorem made the debate clearer than either side alone had made it. Clauser, Aspect, and Zeilinger carried that clarity into experiment. The result is not the humiliation of Einstein. It is the continuation of his seriousness. Einstein wanted to know what reality demanded. The experiments answered, not the way he hoped, but in the spirit of the question he asked. That is a more respectful and more truthful way to see it. Einstein's challenge helped make the discovery possible. His resistance became part of the path to deeper evidence. The universe often advances through such tension. A great mind refuses an easy answer. Another great mind finds a theorem. Others build experiments. The answer arrives slowly. This answer was quantum. And yet, there is still tenderness in the old dream. A local, definite universe is easier to imagine. It feels safer. It feels like the world of familiar objects and familiar causes. But the real universe does not owe us that simplicity. It gives us something else. A world where a photon can be entangled with another photon. A world where the whole can carry information absent from the parts. A world where individual outcomes are unpredictable, but correlations are exact in their statistical form. A world where distance prevents communication faster than light, but does not reduce entanglement to ordinary separateness. A world where the deepest order is not the order of little hidden cards, but of quantum states. The experiments brought this world into focus, and once seen, it could not be unseen. The laboratory tables, the photon sources, the detectors, and the inequalities became part of a larger story about what reality is. Not only what we know about it, but what kinds of explanations are possible. Bell had shown that the old hidden instruction story had a measurable limit. The experimenters showed that nature passes beyond it. This is the central revelation. Quietly, precisely, repeatedly. The particles do not behave as if they were carrying ordinary local answer sheets. Their correlations belong to the entangled state. The universe keeps the whole. The pieces alone do not tell the whole story. As the experiments matured, the implications widened. Entanglement became one of the defining differences between quantum and classical information. It became essential for quantum teleportation. It became important for secure communication. It became a candidate ingredient in future quantum networks. It became a tool for studying complex quantum matter. It became relevant to questions about black holes and space-time. The small experimental clicks opened into the largest questions. This is fitting, because quantum entanglement has always been small and vast at once. It concerns particles, but it challenges reality. It occurs in laboratories, but it may be woven into the fabric of the universe. It can be described with equations, but it changes the meaning of separateness. The experimental story is the moment the mystery becomes undeniable, not fully explained, but undeniable. After Bell tests, one can no longer honestly say that entanglement is merely a philosophical preference. It is an observed feature of nature. It creates correlations beyond classical limits. It is a physical fact. The meaning remains open in some ways. The reality of the phenomenon does not. A pair of entangled particles is not like two gloves in boxes. It is not like two cards in envelopes. It is not like two clocks secretly synchronized. It is not an ordinary shared secret from the past. It is a shared quantum state. And that shared state leaves a pattern in the world, a pattern the experiments have seen. As the story moves onward, the focus begins to widen again. The experiments have answered Einstein's immediate challenge. They have shown that local hidden variables cannot explain the quantum correlations. But they also open a new question. If entanglement is real, and if it is useful, how far does it reach? Can entanglement build new technologies? Can it connect quantum computers? Can it protect information? Can it reveal something about black holes? Can it help explain why space-time itself has the shape it has? Can the deep structure of the universe be understood not only through objects, but through relationships? The experiments do not answer all of this. They open the door. Beyond the door lies the entangled universe. But before walking through, it is worth staying one final moment with the experimental answer itself. Two particles are created together. They move apart. Measurement settings are chosen. Detectors wait. Each result alone is random. The records are compared. Bell's boundary is crossed. A local hidden variable world fades. Quantum reality remains. No signal outruns light. No simple classical story returns. The universe is lawful, but not classical. It is ordered, but not in the way the old picture imagined. It is connected, but not in a way that can be used to whisper instantly across the stars. It is stranger than Einstein hoped, more subtle than simple mysticism, more precise than metaphor, and deeper than ordinary separateness. In the darkness of the laboratory, the detectors click. In the silence between the clicks, an old question is answered. Reality is not built only from separate things carrying hidden instructions through space. At its deepest tested level, nature allows shared quantum states. The whole can matter more than the parts. And through entanglement, the universe reveals that distance, while real, is not always the same as separateness. The experiments had answered one of the deepest questions in physics, but they had not made the mystery disappear. They had shown that entanglement is not only a strange idea in equations, it is not merely a thought experiment. It is not simply a philosophical discomfort from the early days of quantum mechanics. Entanglement is a real feature of the world, seen in laboratories, tested through Bell inequalities, confirmed again and again through the quiet gathering of data. Two particles can share a quantum state. Their measurement results can be correlated in ways no simple local hidden variable picture can explain. No useful message travels faster than light. No signal can be controlled and sent instantly across space. And yet, the old idea of a universe made only from separate little things, each carrying its own complete set of local properties, cannot survive unchanged. This is where the story becomes wider. At first, entanglement was a problem. Then it became a test. Then it became evidence. And now it has become a resource, a thing physicists do not only wonder about, but use. This transformation is one of the quiet marvels of modern science. The feature Einstein found so troubling, the strange link that seemed almost too unsettling to accept as complete, is now one of the foundations of quantum information. It is studied, created, protected, transmitted, and measured. Laboratories around the world work to preserve it with delicate care. Engineers try to use it. Theorists try to understand it. Cosmologists and black hole physicists wonder whether it reaches even deeper than anyone first imagined. Entanglement has become a doorway, not only into the microscopic world, but into the meaning of information, space, time, and reality itself. To understand why, it helps to begin with information. Information may sound abstract, like something written in books or stored in computers or carried in thoughts. But information is always physical. A word on a page exists because ink or pixels are arranged in one way rather than another. A bit in a computer exists because a tiny physical system has one state instead of another. A memory in a brain is tied to physical patterns in living tissue. A signal traveling through a wire or fiber is carried by electricity or light. Information is not separate from the universe. It lives in matter and energy. Classical information is often described in bits. A bit can be 0 or 1. It can be off or on. It can be yes or no. Modern computers are built from enormous numbers of such bits, arranged and processed in patterns so fast and complex that they become images, words, calculations, music, and memory. Quantum information is different. Its basic unit is called a qubit. A qubit can be measured to give outcomes like 0 or 1, but before measurement, it can exist in a superposition of possibilities. It can carry a quantum state that is not merely one classical option or the other, and when multiple qubits interact, they can become entangled, forming shared states that cannot be reduced to the separate state of each qubit alone. This is the heart of quantum information. A quantum computer is not powerful simply because a qubit is both 0 and 1 in a magical way. That is too simple and often misleading. The real power comes from the careful use of superposition, interference, and entanglement. Quantum possibilities can be arranged so that wrong paths cancel and useful paths reinforce. Entangled qubits can hold patterns of correlation that classical bits cannot imitate efficiently. The idea is subtle. A quantum computer does not solve every problem instantly. It does not replace all classical computers. It is not a machine that tries every answer in an ordinary parallel universe and hands us the right one. But for certain kinds of problems, especially those involving quantum systems, some mathematical structures, and certain forms of search or simulation, quantum computers may one day offer extraordinary advantages. One of the most natural uses is simulating quantum matter itself. Atoms, molecules, materials, chemical reactions, superconductors, and quantum fields are difficult for classical computers to simulate exactly because quantum systems grow enormously complex as they become larger. Entanglement is one reason for this complexity. The state of many quantum particles cannot always be broken into simple independent pieces. The whole becomes too rich for ordinary computation to track easily. A quantum computer built from quantum parts may be better suited to simulating such systems. In a sense, one quantum system can be used to understand another. Nature can be asked to calculate nature. This possibility is still developing, and the engineering is difficult. Qubits are fragile. They lose their quantum behavior when they interact too strongly with the environment. Heat, stray electromagnetic fields, vibrations, imperfect controls, and unwanted measurements can disturb them. Entanglement can be lost. Superpositions can fade. Errors can spread. This process, in which delicate quantum behavior becomes entangled with the surrounding environment and loses its usefulness for a controlled experiment, is connected to decoherence. Decoherence is one reason the ordinary world appears classical. It is also one of the greatest challenges in building quantum technologies. To build a useful quantum computer, scientists must isolate qubits enough to preserve their quantum states, but also control them enough to compute. They must create entanglement deliberately, then protect it from noise. They must correct errors without directly measuring and destroying the quantum information they need. They must make systems that are delicate and stable at the same time. This is not easy. But the difficulty itself shows how real entanglement is. A vague metaphor does not need protection from heat and noise. A real quantum resource does. Entanglement is fragile because it is physical. It can be created. It can be damaged. It can be shared. It can be consumed. It can be used. Quantum cryptography is another place where quantum ideas become practical. The goal is secure communication. In ordinary cryptography, secrecy often depends on mathematical difficulty. A message is protected because it would take an attacker too long to break the code with available tools. Quantum cryptography, in some forms, uses the laws of physics more directly. In quantum key distribution, two parties can create a shared secret key using quantum states. If an eavesdropper tries to intercept and measure those states, the act of measurement can disturb them in a detectable way. This does not mean quantum cryptography makes all communication magically unbreakable. Real devices have imperfections, and security depends on careful implementation. But the principle is powerful. Quantum measurement itself can reveal intrusion. Entanglement can also be used in secure communication schemes. Two distant observers can share entangled particles and use their correlations to help generate secure keys. Because the correlations are rooted in quantum mechanics, and because measuring quantum systems changes what can be known, entanglement becomes part of a new way to think about trust, secrecy, and information. Here again, the old philosophical mystery becomes technology. The same strange correlations that troubled Einstein may help protect messages. The same Bell inequalities that tested local realism can be used to verify that devices are truly sharing quantum correlations. A question about reality becomes a tool for security. Quantum teleportation is perhaps the most famous application of entanglement and also one of the most misunderstood. The word teleportation suggests science fiction, a person vanishing in one place and appearing in another, or an object crossing space without traveling. Quantum teleportation is not that. It does not move matter instantly. It does not transport a body, a planet, or a machine. It does not allow faster than light travel. Quantum teleportation transfers a quantum state. Suppose one particle carries an unknown quantum state. The goal is to recreate that state in another particle far away. Quantum mechanics says the state cannot simply be copied perfectly. This is known as the no-cloning theorem. An unknown quantum state cannot be duplicated at will because quantum information is not like an ordinary page of text that can be photocopied without disturbance. But if two observers share an entangled pair, and if one observer performs a special joint measurement on the unknown state and their half of the entangled pair, then the distant particle can be transformed into the original quantum state once the result of the measurement is sent through an ordinary classical channel. That classical message is essential. It travels no faster than light. Without it, the distant observer cannot complete the process. So quantum teleportation does not violate relativity, but it still reveals something extraordinary. The quantum state is transferred through a combination of entanglement, measurement, and ordinary communication. The original state is not copied. It is destroyed at the sending side and reconstructed at the receiving side. The information has moved, but not in the familiar way of carrying a physical object through space. This is one of the clearest examples of how quantum information differs from classical information. A state is not a simple thing. It cannot always be read without disturbance. It cannot always be copied. It can, however, be teleported under the right conditions. Entanglement makes that possible. And so the strange link between particles becomes part of a method for moving quantum information across distance. Entanglement also allows something called entanglement swapping. Imagine two separate entangled pairs. Particle 1 is entangled with particle 2. Particle 3 is entangled with particle 4. Now particles 2 and 3 are brought together and measured in a special way. As a result, particles 1 and 4 can become entangled, even though they may never have directly interacted. This is deeply strange when first heard. Two particles that never met can become linked because of a measurement performed on their partners. But again, no faster than light message is sent. The full result is only known when the necessary classical information is compared. The process is precise, physical, and experimentally demonstrated. Entanglement swapping may be important for future quantum networks. In ordinary communication networks, signals can be amplified and repeated, but quantum states cannot simply be copied and boosted in the same way because unknown quantum information cannot be cloned. To send quantum information over long distances, physicists imagine quantum repeaters. These would use entanglement, storage, swapping, and error correction to extend quantum links across large scales. A future quantum internet, if built, would not simply be a faster version of the ordinary internet. It would connect quantum devices using entanglement and quantum states. It might allow secure communication, distributed quantum computing, improved sensors, and new scientific experiments linking distant quantum systems. Such a network is still a developing goal. But the idea shows how far the story has moved. Entanglement began as a discomfort at the edge of theory. Now it is a possible infrastructure. A hidden relation between particles may one day become part of the architecture of communication. Still, the more entanglement becomes useful, the more important it is to remember what it does not do. It does not allow people to send thoughts instantly. It does not prove that consciousness controls the universe. It does not mean every object is magically communicating with every other object. It does not erase distance. It does not permit faster-than-light signaling. Its power is subtler. It creates correlations and shared states that classical physics cannot reproduce. It allows quantum information tasks that would otherwise be impossible. It changes what can be known, copied, transmitted, and secured. It reveals that the physical state of a whole system can contain information not present in the separate parts. The truth is quieter than fantasy, and more beautiful. Entanglement is also becoming important in precision measurement. Quantum sensors can use entangled states to measure time, fields, forces, or motion with sensitivity beyond what classical systems can achieve in some cases. Entangled atoms can improve clocks. Quantum correlations can reduce certain kinds of noise. Carefully prepared quantum states can help detect tiny changes in gravity, magnetism, or acceleration. In this way, entanglement becomes not only a tool for communication or computation, but a tool for listening to nature more precisely, listening for faint signals, listening for subtle fields, listening for the smallest changes in the physical world. Again, the pattern repeats. A strange foundation becomes a practical instrument. But entanglement does not only point toward technology, it also points back toward the deepest questions. What is the universe made of? Not just matter and energy, not just particles and fields, but relationships, correlations, states that belong to wholes. Some physicists now wonder whether entanglement may be connected to the structure of space-time itself. This idea is still developing and must be treated carefully. It is not a settled fact that space-time is made of entanglement. But in some areas of theoretical physics, especially in studies of black holes, quantum gravity, and holography, entanglement appears again and again as a clue. Black holes are among the places where quantum mechanics and gravity meet most sharply. A black hole has an event horizon, a boundary beyond which light cannot escape. According to general relativity, a black hole is a region where space-time is curved so strongly that all future paths inside the horizon lead inward. But quantum theory adds new questions. What happens to information that falls into a black hole? Is it destroyed? Is it preserved? How does Hawking radiation carry energy away? Can a black hole evaporate, and if so, what happens to the quantum information of what formed it? This is the black hole information problem. It has troubled physicists for decades. Quantum mechanics says information should not simply be destroyed. The evolution of quantum states should preserve information in a deep sense. But black holes seem, at first glance, to hide information behind horizons and perhaps radiate thermally in a way that loses details. This creates a tension between quantum mechanics, gravity, and thermodynamics. Entanglement lies at the heart of the tension. Hawking radiation involves quantum fields near the horizon. Particles and fields outside and inside the black hole can become entangled. The radiation emitted by a black hole may be entangled with degrees of freedom behind the horizon or with earlier radiation. Understanding how these entanglements change over time is central to modern attempts to solve the information problem. The details are difficult, but the larger meaning is clear. Entanglement is not only a laboratory phenomenon, it may be essential to understanding the fate of information in black holes. And black holes are not small philosophical puzzles, they are real astrophysical objects. Some form from collapsed stars. Some sit in the centers of galaxies, millions or billions of times more massive than the Sun. They shape galaxies, power quasars, bend light, and merge in events that send gravitational waves across space-time. In such extreme places, entanglement may help guide the path toward quantum gravity. Quantum gravity is the still unfinished theory that would unite quantum mechanics with general relativity. General relativity describes gravity as the curvature of space-time. Quantum mechanics describes matter and energy through states, probabilities, and fields. Both theories work extraordinarily well in their own domains, but they do not yet form a complete, unified picture. Black holes and the Big Bang push both theories to their limits. Inside black holes, gravity becomes extreme. Near the beginning of the universe, density and energy were extreme. In such places, quantum effects and gravity both matter deeply. Entanglement may be one of the clues to unification. In certain theoretical frameworks, the geometry of space-time seems related to patterns of quantum entanglement. In holographic ideas, a gravitational universe in one description can be related to a quantum theory without gravity in fewer dimensions. In these relationships, the entanglement structure of the quantum theory can correspond to the shape and connectivity of space-time in the gravitational picture. This is one of the most astonishing ideas in modern physics. The shape of space may be connected to quantum information. Distance itself may not be as fundamental as it seems. Again, this is not fully settled as the description of our universe. It is an active field of research, rich with mathematics, evidence from theoretical models, and open questions. But the direction is profound. Entanglement, once dismissed by some as only a philosophical oddity, may be connected to the emergence of space-time. If true in some deep sense, then entanglement is not just something that happens inside the universe. It may help explain why the universe has the connected shape it does. The relationship may come before the distance. This echoes the core mystery in a larger key. At the level of two particles, entanglement suggests that the whole may be more fundamental than the separate parts. At the level of space-time, some theories suggest that the connections between quantum degrees of freedom may help give rise to the geometry in which things appear separated. The same theme returns. Parts and wholes, separation and relation, distance and connection. The visible world feels like a collection of things arranged in space. The quantum world whispers that relationships may be deeper. There is a famous phrase in modern theoretical physics, often shortened to ER equals EPR. It refers to a speculative connection between wormholes, represented by Einstein-Rosen bridges, and entanglement, represented by the Einstein-Podolsky-Rosen paradox. The idea suggests a deep relationship between certain kinds of space-time connections and quantum entanglement. It does not mean ordinary, entangled particles are connected by usable wormholes in the science fiction sense. It does not mean one can travel through entanglement. But it shows how deeply the language of geometry and entanglement have begun to intertwine. Even the names carry history. Einstein appears on both sides. Einstein-Rosen bridges from general relativity. Einstein-Podolsky, Rosen correlations from quantum foundations. The same mind that resisted quantum non-locality also helped create the theory of space-time, in which modern physicists now search for deeper connections between gravity and entanglement. There is a strange elegance in that. Einstein's questions did not close. They multiplied. They moved from photons and measurements to black holes and space-time, They move from the discomfort of spooky action to the possibility that space-time itself may be woven from quantum correlations. Whether that idea is ultimately true or only a stepping stone, it shows how far entanglement has traveled, from paradox to experiment, from experiment to technology, from technology to the possible fabric of reality. The story also changes how we think about the word empty. In classical imagination, empty space is just a container. It is the stage on which matter moves. Things are placed within it, separated by distances. Space itself is mostly nothing. Modern physics has already changed that. In relativity, space-time is dynamic. It can curve, expand, ripple, and respond to mass and energy. In quantum field theory, the vacuum is not simple nothingness. Fields still exist. Quantum fluctuations occur. Particles can appear as excitations of underlying fields. Entanglement deepens the change. Even the vacuum of quantum fields contains entanglement between regions of space. The fields in one region are not entirely independent of the fields in another. The ground state of a quantum field is not a simple empty state with nothing happening. It contains structured correlations. The emptiness between things is not as empty as it appears. The universe is relational even in its quietest states. This does not mean space is full of hidden messages or mystical energy in the ordinary sense. It means that the quantum vacuum has mathematical structure, and that entanglement is part of that structure. The calm background of reality is more intricate than common sense expects. Again, the theme returns. The visible surface is simple. The hidden foundation is subtle. The night sky looks like stars separated by darkness, but the darkness itself belongs to space-time, quantum fields, radiation, gravity, dark matter, dark energy, and perhaps patterns of entanglement deeper than ordinary perception. The universe is not only a collection of bright points, it is a fabric of relationships. Entanglement also teaches something about knowledge. In classical physics, one can imagine learning more and more about each part until the whole is understood. If knowledge is incomplete, it is because information is hidden. Reveal the hidden information and uncertainty disappears. Quantum mechanics changes this. There are limits to what can be known together. Some properties cannot be simultaneously definite in the classical sense. Measurement choices matter. An unknown quantum state cannot be copied perfectly. Entangled systems can have a well-defined joint state while their parts individually appear uncertain. Knowledge in quantum mechanics is not merely a smaller amount of classical knowledge. It is a different structure. Sometimes the whole is known while the parts are not. Sometimes measuring one property prevents definite knowledge of another. Sometimes the best possible description gives probabilities, not hidden certainties. This can feel unsettling, but it can also feel peaceful. The universe is not obligated to be completely graspable in the form our intuition prefers. It may be graspable in a deeper mathematical form, one that preserves law, pattern, and prediction while refusing certain classical images. The quantum world is not a failure of order. It is a different order. Entanglement is one of its purest expressions. The particles do not need to carry little cards with answers written on them. The pair carries a state. The results appear when measurements are made. The correlations emerge when records are compared. The law is not in each isolated piece, it is in the whole pattern. This idea reaches beyond physics as a metaphor, though the physics should remain clear. Entanglement in the scientific sense is precise and should not be casually applied to everything. Human relationships are not quantum entanglement. Memories, emotions, and shared histories are not Bell test correlations. The word should not be blurred until it means any connection at all. But as a scientific fact, entanglement can still change how we imagine reality. It reminds us that separateness is not always fundamental. It reminds us that the whole can matter. It reminds us that what seems random locally can become meaningful in a larger comparison. It reminds us that distance, while real, is not the same as classical independence. There is comfort in that, not because it proves any mystical unity, but because it shows that the universe is more deeply structured than it appears. The cosmos is not loose dust, it is patterned. From quantum states to galaxies, from atoms to black holes, from photons to space-time, structure appears at every scale. At the cosmic scale, gravity gathers galaxies into clusters and filaments. At the quantum scale, entanglement gathers systems into shared states. The two are not the same phenomenon, but both challenge the idea that the universe is merely a pile of separate objects. The universe is made of relations as well as things. This may be one of the quiet lessons at the end of the journey. We began with the ordinary world. Stones, stars, planets, distance, cause and effect. Then, the quantum world opened. Light behaved as wave and particle. Matter became probability. Superposition softened definite properties. Measurement became part of the story. Two particles became one shared state. Einstein objected. Bohr answered. EPR sharpened the paradox. Bell drew the boundary. Experiments crossed it. Entanglement became real, tested, and useful. Now the question widens again. What else is built from this strange fabric? Quantum computers may use entanglement to process information in ways classical machines cannot. Quantum communication may use entanglement to protect secrets and connect distant devices. Quantum teleportation shows that quantum states can be transferred through entanglement and classical messages. Quantum sensors may use entanglement to measure the world with extraordinary delicacy. Black hole physics may depend on entanglement to preserve information. Space-time itself may, in some still mysterious way, be related to patterns of entanglement. The journey ends not with a closed answer, but with a larger horizon. That is fitting. Quantum entanglement has never been a simple destination. It is a doorway that opens into more doors. Each answer reveals a deeper question. The experiments answered Einstein's local hidden variable hope with remarkable clarity. But they did not erase the deeper puzzle of what quantum reality means. The technologies show that entanglement can be used. But they do not reduce it to something ordinary. The theories suggested may reach into space-time, but they are still being explored. Entanglement remains both fact and mystery. That balance is rare and beautiful. It is real enough for engineering, strange enough for philosophy, precise enough for experiments, deep enough for cosmology. At the end, it is worth returning to the simplest image. Two particles are created together. For a moment, they belong to one shared quantum state. They move apart. Space opens between them. Perhaps the distance is a meter, perhaps a kilometer, perhaps far more. Each particle is measured. Each result alone is unpredictable. But the two results, when compared, reveal a pattern that no local hidden instruction story can explain. Nothing visible passes between them. No message is sent faster than light. No observer controls the distant result. And yet, the relationship remains. The whole has not been fully broken into parts. This is the quiet mystery. A mystery not of noise, but of structure. Not of magic, but of law. Not of fantasy, but of experiment. The universe is telling us that the deepest level of reality is not built exactly like the world of tables and stones. The familiar world is real, but it is not fundamental in the way it first appears. Beneath it lies a quantum order, precise and strange, where possibility, measurement, and relationship play roles that common sense never expected. And from that order comes everything familiar. Atoms, chemistry, light, matter, stars, planets, life, thought. The mind that wonders about quantum entanglement is itself made from quantum matter arranged into a warm, living structure. The brain does not need exotic quantum magic to think, but it exists because atoms, chemical bonds, and electromagnetic interactions obey quantum laws. The mystery we study is not outside us. It is part of the foundation from which we are built. When we look into the night sky, we see distance, the moon far above Earth, planets wandering across constellations, stars scattered through the Milky Way, galaxies separated by millions and billions of light years. The universe appears to be a vast arrangement of separated things, and on many scales, that is true. Distance matters. Light takes time to travel. Signals are limited. Galaxies are far away. The Andromeda Galaxy is not here. A star on the other side of the Milky Way is not beside us. Relativity preserves the causal order of space-time. But quantum entanglement adds another truth. Separation is not always the whole story. At the deepest tested levels, nature can describe distant systems through one shared state, not in a way that lets us escape time, not in a way that lets us send messages instantly, but in a way that changes what it means for things to be independent. The universe is both separated and connected, both local in its signaling and non-classical in its correlations, both familiar and strange. This is why entanglement remains so powerful as an idea. It does not destroy the everyday world, it deepens it. The moon still rises. The sun still shines. A stone still rests in the hand. But beneath those ordinary truths lies another truth, quieter and more delicate, in which particles and fields obey rules that stretch the imagination. Science does not remove wonder from the world. It gives wonder sharper edges. Entanglement is not a vague awe. It is a measured violation of classical limits. It is a resource for quantum information. It is a clue in black hole physics. It is a possible thread in the fabric of space-time. It is a reminder that reality is not required to be simple. The old classical dream was beautiful. A universe of definite properties, local causes, hidden mechanisms, and perfect predictability. But nature gave us something else. A universe where probability is fundamental, at least in the standard view. A universe where measurement matters. A universe where the whole can be more than the sum of its parts. A universe where correlations can exceed classical bounds. A universe where information and physics are inseparable. A universe where the deepest relationships may be written not in visible threads, but in quantum states. This does not make reality less real. It makes reality more subtle. The story of entanglement is not the story of science losing its grip on the world. It is the story of science holding on carefully enough to follow the world beyond intuition. It is the story of physicists refusing easy answers, building delicate experiments, accepting strange results, and turning mystery into knowledge without making the mystery vanish completely. There is humility in that. And peace. The universe does not need to be forced into the shape of human expectation. It can be allowed to be what it is. We can measure it, test it, question it, and still let it remain deeper than our first images. The particles drift apart. The detectors wait. The records are compared. The hidden pattern appears, and from that pattern, a new vision of reality slowly rises. Not a world of isolated fragments, not a world of instant messages, not a world of supernatural connection, but a quantum world. A world where relationships can be physical. A world where information has laws. A world where space and separateness may not be the deepest starting point. A world where the whole sometimes comes first. Perhaps, in the far future, quantum networks will stretch across continents, linking devices through entanglement. Perhaps quantum computers will help reveal new medicines, new materials, or new laws of nature. Perhaps black hole research will show that space-time itself emerges from quantum correlations. Perhaps a deeper theory will explain measurement, gravity, and information in one unified language. Or perhaps the future will be stranger still. The history of entanglement suggests caution. Again and again, nature has been deeper than expected. Light was not simply a wave. Matter was not simply made of tiny, hard pieces. Measurement was not passive. Probability was not mere ignorance in the old way. Entanglement was not a philosophical curiosity. Bell's theorem was not only mathematics. Laboratory clicks were not only laboratory clicks. The universe kept revealing deeper structure. It may do so again. Somewhere in a quiet laboratory, photons are still being entangled. Atoms are being cooled nearly to absolute zero. Ions are being trapped. Qubits are being controlled. Detectors are waiting in darkness. Computers are correcting quantum errors. Satellites are testing quantum links. Theorists are writing equations about black holes, information, and space-time. The story is not finished. Entanglement is no longer only Einstein's spooky problem. It is one of the central languages of modern physics, and yet the old phrase still lingers because it captures something human. The feeling of standing before a result that is real, tested, and still difficult to picture. The feeling of seeing the universe refuse a simple answer. The feeling of discovering that what seems separate may, in the right quantum sense, belong to one state. Spooky action at a distance was Einstein's discomfort. Quantum entanglement is nature's fact. Between them lies one of the greatest journeys in science. From unease to theorem, from theorem to experiment, from experiment to technology, from technology to the possible foundations of space-time. And still, at the center, the image remains simple. Two particles, one shared state, distance between them, randomness alone. Ordered together, a universe that cannot be reduced to the old picture, a reality where the hidden connections are not made of ropes or signals, but of quantum information. In the calm darkness of space, stars shine across impossible distances. Their light travels patiently, obeying the speed limit of the universe. Galaxies drift in the expanding cosmos. Black holes bend space-time. Atoms form molecules. Planets circle suns. And beneath all of it, in the small and silent structure of matter, the quantum world continues. Particles interact. States evolve. Entanglement appears and disappears. The environment spreads correlations. The classical world emerges. The ordinary world rests on the extraordinary. Perhaps that is the final quiet thought. Reality is not less beautiful because it is strange. It is more beautiful because the strangeness is real. The universe does not only contain mystery and distant galaxies or black holes or the beginning of time. It contains mystery in the smallest measurable systems, in a pair of photons in a spin state, in a detector click, in the comparison of two records. A shared state, a measurement, a correlation, a theorem, a quiet answer from nature, and through that answer the universe tells us something gentle and profound. Distance is real, but separateness is not always complete. The world is lawful, but not always classical. The parts matter, but sometimes the whole speaks first. And in that strange and delicate truth, quantum entanglement remains one of the most beautiful mysteries ever found.